Hi, this is a complete lesson in thermodynamics focused on Edexcel IAL Unit 5. Before watching this video, see the description of this video. There already I have done a complete lesson on cosmology, in cosmology, and 3 lessons in nuclear decay. So I discussed it in 3 lessons. First lesson, binding energy. Second lesson, radioactive decay. And the third lesson, nuclear transformation, that is nuclear fission and fusion. So all these lessons are already done. I'll give the URL or the link for these lessons, cosmology and complete lessons of nuclear decay are given in the description of this video, the URL or the link, so you can follow them. Also, by using the playlist of this channel, you can navigate to any lesson you would like to watch. Okay, so this is thermodynamics. I'll try to complete in one lesson the whole thermodynamics. So mainly it consists of 3 main topics. First one is specific heat capacity, then latent heat, then gas and gas laws. Yeah, those are the topics in your syllabus. Okay, first you must know what is temperature and what is heat. Okay, in IGCSE you learn that all substances are made of particles. We normally say particles means they are made of atoms and molecules. Certain elements are made of atoms. For example, when you consider sodium, due to metallic bonds, the atoms are bound together. Like that, there are certain elements or certain substances, they are made of molecules. So in physics, we don't distinguish like atoms, molecules. We say sometimes particles. So we know all the substances are made of particles. So the particles have intermolecular force. That force keeps the particles together. And those particles could vibrate, or they could have a rotational motion or translational motion, that is a linear, like a motion, random motions, right? You learn that in IGCSE also. In solids, particles vibrate, oscillate about a point. In liquid, the particles slip over each other. And in gases, particles are more free to have translational motion, but there will be collision among them. Like that we learned in IGCSE. Okay, so due to this motion and due to intermolecular forces, particles possess energy. Due to motion, could be a vibration or oscillation, that possess kinetic energy. Due to intermolecular force, there will be potential energy. Right, so now we'll come to the point, what is temperature, what is heat. You should be able to distinguish these 2 physical quantities. You know the units of them, but you should be able to distinguish heat and temperature. Actually, what is temperature? Temperature is the measurement of. So what is temperature means? Temperature is the measurement. First you must know this. I can put it as the first point you must know. If I do it in point format, focus on exam. So first point, you must know what is temperature. Temperature is the measurement of average kinetic energy of the particles. Remember that. Temperature is the measurement of average kinetic energy of the particles, because when you consider a substance, 1 mole of substance consists of Avogadro number of particles. Different particles will have different speed, different kinetic energy at that moment. So that's the reason we say average. So temperature is the measurement of average kinetic energy of the particles. Then what is heat? So the unit of temperature, you learned that in IGCSE also. The unit of temperature we normally use degree Celsius or Kelvin. The relationship between Kelvin and Celsius, that is to convert Celsius to Kelvin, we add 273.15. So that means Celsius scale plus 273.15, but normally we don't consider 0.15. So for simplicity we add 273, then we will get the Kelvin scale. Kelvin scale. So for example, 25 degrees Celsius means how much in Kelvin? 273 plus 23, 273 plus 25 Kelvin. So that will be equal to 298 Kelvin. But when we consider change in temperature, temperature could be increased or decreased. Change in temperature will have the same numerical value. For example, temperature of a substance, then you must know the change in temperature is the same in both, the numerical value is the same in both scales. For example, temperature of an object increases from temperature is denoted by capital T. You are using these things for a long time in O level also. So delta T indicates the change in temperature. So that means it increases from 25 degrees Celsius to 37 degrees Celsius. So 37 degrees Celsius minus 25 degrees Celsius is the change in temperature. If you give it in Celsius, it's going to be 12 degrees Celsius. But if you try to find it in Kelvin, what should I do? Careful, it's a very common mistake students they do when they want to find the change in temperature in Kelvin, they add 273 with this one. That is wrong. Don't do that way. You have to find the both temperatures in Kelvin scale. So that is 273 plus 37. That's the initial final temperature minus 273 plus 25. So this is the final temperature in Kelvin scale. This is the initial temperature in Kelvin scale. When you subtract 273 will get cancelled, but you will get the same answer, 12 Kelvin here. You will get 12 Kelvin here. So the change in temperature will have the same magnitude, the numerical value in both scales, that is Celsius scale and Kelvin scale. You must know. Don't make careless mistake or the common mistake students they make. They add 273 with this value. That is wrong. Okay, so I told the 2 points you must know. First, the important point, temperature. It's a measurement of average kinetic energy of particles of a substance. Then what is the second point? What is heat then? So what is heat? Okay. Heat means it is not energy possessed by a substance. Carefully, it is not an energy possessed by a substance. Actually, what is heat means it's a flow of energy or transfer of energy from one substance or one object to another object due to difference in temperature. Careful. Heat means it is not energy possessed by the object or it is not the energy possessed by the substance. What is heat means? Heat indicates the transfer of energy or flow of energy from one object to another object or one substance to another substance due to difference in temperature. Careful, you must know that heat is the flow of energy or transfer of energy from one substance to another substance due to difference in temperature. That is heat. So what is the SI unit of heat? Heat is measured in joules. This is either degree Celsius or Kelvin we use in your syllabus. But heat is measured in joule. Temperature is the measurement of average kinetic energy of the molecules or particles in a substance. There's a total average kinetic energy of the substance in the average kinetic energy of the particles in the substance. Then heat is the energy flow or transfer of energy from one substance to another substance due to difference in temperature. Due to difference in temperature. Okay, so naturally, how heat flows? So heat is a flow of energy due to the temperature difference. So naturally, how heat flows? Heat flows from object or substance with higher temperature to substance with lower temperature. That's the way heat flows naturally from substance with higher temperature to substance with lower temperature. So that's the way heat flows. But can't we make heat to flow from substance with lower temperature to substance with higher temperature? Yes, possible. But we don't need that. In thermodynamics, we consider that in second law of thermodynamics, we can use these type of situations. For example, it's in refrigerator, you can make the heat to flow from substance or object with lower temperature to substance with higher temperature, but there we need an external work. So in refrigerators, external work is done by the electrical energy or the motor. It does the, refrigerators have motor, there's gas flows. So anyway, that system makes the heat to flow from lower temperature to higher temperature. You can ask me, what do you mean by heat flows from lower temperature to higher temperature in refrigerators? Okay, think about a refrigerator. So initially, before you switch on, inside and outside, the temperature will be the same, room temperature. Maybe the room temperature is 25 degrees Celsius. Okay, now you switch on the refrigerator. So inside the refrigerator, there's a bottle of water that was initially at room temperature 25 degrees Celsius. So what happens, the temperature of the water will gradually decrease from 25 degrees Celsius. Initially it was at 25 degrees Celsius. And when you switch on the refrigerator, the temperature of the water will gradually go down. You can see the sides of the refrigerator gets warmer. So the heat is flowing from refrigerator to outside. But if you think about the net heat flow, now imagine at an instant the temperature of the water has become, initially it was 25, now it has become 18 degrees Celsius. Right. Now if you let it, the function or on the fridge continuously, later the temperature of the water might become around 12 degrees Celsius. How that happens? Now 18 degrees Celsius, from 18 degrees Celsius, the heat is in overall flowing from 18 degrees Celsius to outside 25 degrees Celsius because of work done by the gas. The air flows inside, the cool air will be pumped by the fan inside. So anyway, in overall, the heat flows from the bottle which has 18 degrees Celsius to outside 25 degrees Celsius. That's the room temperature environment outside the refrigerator. So that means here the heat is flowing from lower temperature to higher temperature. How that happens? Because of external work done, something like electric motor. But anyway, you don't need these things. Naturally heat flows from higher temperature to lower temperature. Okay, next thing is internal energy. You must know what is internal energy. I already told that all the substances are made of atoms, molecules. Generally we say particles. So particles have both kinetic energy and potential energy. All the particles, when you consider a substance, say for example 1 mole of substance, all the particles in that 1 mole of substance won't have the same magnitude of kinetic energy at an instant. Same way they won't have the same magnitude of potential energy at an instant. So they will have different magnitudes of kinetic energy and potential energy. So what is internal energy means? Internal energy is the sum of random kinetic energy and potential energy of the particles. Again I am saying, what is internal energy? Internal energy of a substance is the sum or addition of random kinetic energy and potential energy of the particles, you can say of the molecules or atoms of the substance. That is called internal energy. So it has two different types of energy, again kinetic energy and potential energy. Okay, now kinetic energy indicates what? Potential energy indicates what behavior of the substance. Okay, what is the change in kinetic energy causes? I already defined what is temperature. Temperature indicates the average kinetic energy of the particle. So whenever you increase the temperature by transferring heat to the substance, you can increase the temperature, you know that. So by transferring heat to a substance, so there is a substance, maybe a metal block. If you transfer heat to that by using a Bunsen burner or flame, you transfer heat, or when you keep the metal block in near a flame or something like that. When you transfer heat to the substance, what happens? The heat is flowing to the substance. So heat is flowing to the substance means the particles will gain that energy and their kinetic energy will increase. So whenever a substance gain heat, whenever a substance gain heat, there will be increase in temperature. Okay, same way, when heat is absorbed out of that particle or when the heat flows out of that particle, you can make heat to flow from from a substance. How can we make heat to flow out of the substance? If you keep that substance in an open environment, it will lose heat to the surrounding. Or if you keep the substance in a freezer or in a refrigerator, it will lose its heat. Anyway, whatever it is, whenever when it loses heat, what will happen? Decrease in temperature. That means decrease in temperature means, the meaning of decrease in temperature, kinetic energy of the particles will decrease. Better to say average kinetic energy. Average kinetic energy of the particles will decrease when the heat is lost from the substance. Same way, when it increase in temperature means, there I can say average kinetic energy of the particles will increase. Average kinetic energy of the particles will increase. So you must know what happens when a substance or matter or object gains heat and when it loses heat, what will happen to the internal energy. So internal energy will gain means the internal energy will increase. So that means kinetic energy of the particles will increase. When a substance loses heat, decrease in temperature means decrease in kinetic energy of the particles. So the average kinetic energy will decrease. That means internal energy will decrease. Okay, so I already said that change in average kinetic energy of the particles indicates change in temperature. So if the average kinetic energy of the particles of a substance increase means the temperature is increasing. If the average kinetic energy of a particles in a substance is decreasing means temperature is decreasing. Okay, that's all I have discussed it. Now, what is the change in average potential energy of the particles? Yes, potential energy is due to intermolecular force. So change in average potential energy of the molecules means there should be change in intermolecular force. That happens only during state change. So if there is change in average potential energy of the molecules means there is state change is happening. So state change is happening means it's like solid becomes liquid, melting, liquid becomes vapor, vaporizing, or vapor becomes liquid, condensation, or liquid becomes solid, freezing. One of these state changes should happen. So for example, you O-level also you learned that solids are in particles or molecules of the solids are tightly packed together. There is a strong intermolecular force. So if you want to melt a solid, for example, if you want to melt ice into water, so the intermolecular forces should be weakened, then only they will become water. So that means if the intermolecular forces should become weakened means there should be work done to break the bonds. So the break the bonds, there should be work done means what happens? Energy should be supplied, heat should be supplied there, but that heat won't change the temperature. I already told that heat means transfer of energy from matter or substance with higher temperature to lower temperature. I already told that. But during state change also, heat must be supplied to the substance. For example, if you want to melt, the heat must be supplied to the substance. But there won't be any change in temperature. Yes, that's the reason it's called latent heat. I'll discuss it separately after finishing the specific capacity. Latent means hidden. It's not measured. The change in temperature is invisible or it cannot be detected. There is no change in temperature. That's the reason it's called latent heat. Latent means hidden heat. Yeah, anyway, I'll come to that point later. But that means if there is a change in average potential of the molecules, means there is state change. For example, if you want to convert solid to liquid, you have to melt it, means heat should be supplied. So the intermolecular forces should be weakened. So that means work is done on the molecules to weaken the bonds. That means the potential energy, average potential energy will increase. So if the average potential energy will increase, means the substance is changing its state from solid to liquid or liquid to vapor. To convert liquid to vapor, the intermolecular force should become much weaker or almost no intermolecular force. Like that, it should come to that state. So anyway, so when a state change occurs from solid to liquid or liquid to vapor, liquid to gas or whatever it is, the intermolecular forces should become weaker. That means the average potential energy will increase. Average potential energy will increase when solid becomes liquid or liquid becomes vapor. Same way other way, when the liquid becomes solid, freezing, intermolecular force should become stronger. So average potential energy will decrease. So remember that. So the change in average potential energy of the particle, or that refers the change in state, that you must know. Okay, next point you must know thermal equilibrium and steady state. Already I told heat is a energy that flows from object with higher temperature to substance with lower temperature. So what happens, imagine there are two different objects at two different temperatures. This is at a temperature, for example, at 100 degrees Celsius. This is in contact with another object that it is at a temperature of 20 degrees Celsius. So they are in contact. Imagine they are in contact, but they won't lose heat to surrounding. They are in a closed environment such that they are not losing heat to the surrounding. Only they can transfer energy among them. Okay, so imagine a situation like this. So here what happens, higher temperature, lower temperature. So the heat will flow from object with higher temperature to object with lower temperature, or substance with higher temperature to substance with lower temperature. Heat will flow, right? Then what happens, when I told that when an object gains heat, the average kinetic energy of the molecules will increase, so the temperature will increase. When an object or the particles of a substance loses heat, the average kinetic energy of the particles will decrease, so its temperature will decrease. So heat is flowing naturally from higher temperature to lower temperature. So the particles in this object, if I call them the object A, this is B, the temperature of the object A will decrease. The particles are going to lose their average kinetic energy. The particles in B, they are gaining heat, so their average kinetic energy will increase, so their temperature will increase. Imagine something like that. This temperature is higher, this is lower, this is losing, this is gaining. There will be a situation at an instant, both will have the same temperature. Both will reach the same temperature, because this is losing heat, this is gaining heat. So gradually this temperature will drop, this temperature will increase. At an instant, both will have the same temperature. Finally, both will have a temperature that is equal to the same magnitude, or equal temperature, or same temperature. So when the temperature becomes same, both substances or both objects have particles with same average kinetic energy, then there won't be any net heat flow, because both have the same temperature. So at this instant, we say both objects are at thermal equilibrium. Both objects are at thermal equilibrium. That means they have reached a steady state. Steady state means no further transfer of heat. No further transfer of heat. So at that situation, both objects will have the same temperature and they will be in thermal equilibrium. Very important for questions like finding the specific capacity of a metal piece. There are questions in the exam. That means a calorimeter consists of water at room temperature, maybe at 25 degrees Celsius. There's water. We'll do the questions, but I'm just telling. You might given a metal piece, a small metal piece, or few identical metal pieces. All mass, they all have the initial same temperature. Maybe they would have kept in a boiling water, so the initial temperature is 100 degrees Celsius. Then you are dropping all those metal pieces into the water and you close it. So it's a thermal insulation, no heat loss to surrounding. So they can ask to, they can say the final temperature 25 degrees Celsius becomes finally maybe 45 or something like that. Find the specific capacity. So there, the metal piece, those at higher temperature, they are going to lose heat. The heat lost by metal piece is going to gain by both water and the calorimeter. So by using conservation of energy, we can find the final temperature of the whole system. Or if we know the final temperature, we can find the specific heat capacity. I'm going to explain specific capacity. We can find the specific heat capacity of the metal piece, or if we know the specific capacity of metal piece, we can find the specific capacity of the water, or something like that we can do. So there we consider the steady state thermal equilibrium, that is the final state during this experiment. Okay, so next topic is specific heat capacity. Okay, so what is specific capacity? It's the property of a material regardless of temperature, regardless of mass. It's a property of a material that decides the change in temperature of it when it gains or loses heat. For example, we'll think about a simple experiment. You are given same mass of two different types of metal blocks, or maybe this is copper, 1 kilogram of copper block. This is 1 kilogram of aluminium block. Both are same mass. Exactly, both have the same identical thermal insulation, so they don't lose any heat to surrounding. Thermal insulation can be made by using Boyle. And they have identical heater, electric heater with same power. Identical heaters are kept inside. This is copper. This is aluminium. Okay, so they consist of identical heaters, electric heaters connected to electric power supply. I'm not showing it, power supply. So both metal blocks have the identical heaters and have two identical thermometers kept at the same distance from the heaters. Identical thermometers. Right, so it's fully thermally insulated, no heat loss to surrounding. Okay, so identical heaters, identical thermometers, same type of insulation, both have same mass, but only different is different type of material. One is copper, other one is aluminium. Okay, switch on the heater and let it emit heat for the same time period. So the heater is at higher temperature, metal block initially both were at room temperature, maybe 25 degrees Celsius, both metal blocks, copper and aluminium initially, they were at room temperature 25 degrees Celsius. So the heater will transfer heat to the metal block because temperature of the heater is higher. Always heat flow from higher temperature to lower temperature. So let it switch on both metal blocks for the same time period, maybe 2 minutes. Switch off it and record the thermometer readings. You will see the reading of the thermometers will be different because I told that both heaters are identical with the same power. So the heat given by the heaters per second unit time is the same, that is power P. They were switched on for 2 minutes. So the heat given, the energy, heat is a form of energy that flows, power into time. So both were switched on for the same time, 2 minutes, 2 into 60. So both metal blocks receive the same amount of heat, but the change in temperature or increase in temperature will be different. Why? Because both have different atomic structure, different structure of atomic planes. So the vibration of the particles, atoms or molecules will be different. So the change in temperature, that is increase in temperature because of the kinetic energy, will be different when we consider average kinetic energy gained by the particles of the copper or atoms of the copper, and average kinetic energy of the particles or molecules, atoms gained by the aluminium will be different because the atomic plane structures are different. That's the reason the increase in temperature will be different. So that's like that, because if you have same way you can compare 1 kilogram aluminium or 2 kilogram whatever it is, but identical mass we used. So the temperature, change in temperature depends on type of material. So the property that decides the change in temperature of a material is called specific heat capacity of the material. The property of the material, something like what you learned in unit 2, resistivity, Young modulus, they all property of materials. Same way, the property of the material that decides the change in temperature of it when certain amount of heat is given to it or absorbed from it. The change in temperature is decided by the property called specific heat capacity. It's denoted by symbol C. So you know, when we define specific capacity, all the definition we define such that in a mathematical format. So specific heat capacity is defined like this. So several times in the past papers they asked to define specific heat capacity. So we define specific capacity means the amount of heat required to convert 1 kilogram of unit mass of substance through 1 degree Celsius or 1 Kelvin, because I already told that change in temperature will have the same numerical value whether it is in Celsius scale or Kelvin scale. The numerical value will be the same. So that's the way we define the specific heat capacity, amount of heat required to change the temperature of unit mass of substance through unit Kelvin or 1 degree Celsius. That is defined specific heat capacity. So when we define, you don't need to write in terms of words, you can give it in an equation format also. So specific heat capacity equal heat transferred, heat flow, we can say heat flow. It could be heat flown to the substance or heat flown out of the substance, either way, heat flow divided by mass, because unit mass into change in temperature, that is unit change in temperature. So change in temperature, capital T, I put it, temperature I use capital T. So specific capacity denoted by C equal E over mass M delta T. We normally cross multiply, E equal MC delta T. This is the equation. You had it in IGCSE also, A level also, we use the same equation. So the unit of C, this is unit of E, normally we keep it in joules or kilojoule, but there are many possibilities are there, joule. This could be either degree Celsius or Kelvin. Mass, normally we keep it in kilogram or gram or kilogram, but normally depending on the question you can find out gram or kilogram. So the unit of C will be, when you use joule per kilogram, joule per kilogram per degree Celsius or joule per kilogram per Kelvin, or if you keep it in joule, gram, joule per gram per degree Celsius or joule per gram per Kelvin. Either way we can use, no problem, but normally we use either joule per kilogram per Kelvin or joule per kilogram per Celsius. Sometimes if the energy flow is larger, we put kilojoule per kilogram per Celsius or kilojoule per kilogram per Kelvin. Either way we can use it. So there are many possibilities. So when you are getting questions, you have to use according to the given quantity. For example, if the specific capacity is given in joule per kilogram per Celsius, and they are asking to find the energy required, but the mass is given in Gram means we have to convert the mass to kilogram such that the unit tallies. You know that's not a big issue. Okay, so this is the practical measuring the specific capacity of metal block. First measure the mass of the metal block without heater and the thermometer. So measure the initial mass of the metal block, let it be m. Then complete the setup as shown in the diagram. Record the initial temperature of the thermometer, that will be the room temperature. We'll say that is Ti, that's the initial temperature. Then complete the circuit as shown in the diagram and switch on there should be a good thermal insulation. You can cover it with wool or you can keep it in a sawdust. Then complete the switch on the circuit. Record the voltmeter ammeter reading if you don't know the power output of the heater. But if you know the power output of the heater, you don't need voltmeter ammeter. There won't be any big there won't be any significant change in the current and voltmeter mostly. So if you don't know the power of the heater, you must have voltmeter ammeter. So power of the heater is voltage, voltmeter connected across the heater. So that records the voltage applied to the heater, ammeter records the current, so P equal VI. From that you can find the power input to the electrical power input to the heater. Mostly the heaters are 100% efficient. There is no other form of energy output, so input power could be taken as equal to output power. So there you can consider the power emitted by the heater also V into I, voltmeter reading into ammeter reading. Okay, so you should know the power of the heater. This variable resistor is connected in case if there are any changes in the ammeter reading due to change in resistance of the heater, but that won't happen that much. So if there are any changes, you have to maintain the voltmeter ammeter reading constant by using the variable resistor. Okay, so the initial temperature is recorded, mass is measured, then every known interval, say for example depending on the power of the heater, you can measure the temperature of the metal block every 3 minutes or 4 minutes interval, like that. During every known time period, measure the relevant temperature of the metal block. So this is time temperature of the metal block. You can measure it at different known time intervals. Okay, you have set of reading, you can take around 15 readings at different temperature, different time periods. That is, maintain the time interval the same every 2 minutes or 5 minutes depending on the power of the heater. Okay, so here the finally, it's completely depends on conservation of energy. Heat is given out by heater. There is no heat loss to surroundings, so all the heat given out by the heater is absorbed by the metal block. So we can write an energy equation: heat given out by heater, heat emitted by the heater, is equal to heat absorbed by metal block. So heat given by the heater at time t, power into t, P into T, is it? Energy, heat is a form of energy. So that is power into time, P into T. We know the power. If you don't know power, that is P equal VI. That is equal to mass of the metal block, we measure it M. The specific heat capacity we are going to calculate C. So during time t, the temperature is T, the initial temperature Ti. So the change in temperature delta T is the temperature at time T is capital T, and Ti is the initial temperature. So the change in temperature during time T is T minus Ti. Okay, so here the variables are temperature and the time. When the time changes, when the time passes, the final temperature of the metal block or the reading of the thermometer will be different. So they are the two variables. So this is the independent variable. Time is the independent variable. T is the dependent variable. So we should plot the T on y-axis. So P is a constant, M is a constant, C is a constant. So you can divide the whole equation by MC. So it will become P over MC into T is equal to T minus Ti. So make the t subject because that is a dependent variable. So t is equal to p over mc times t plus ti. This is in the form of y equal p is a constant, m is a constant, c is a constant. So this is going to be a gradient. So we normally put gradient by m. Don't get confused with this m and m. Or I'll put the mass as m naught. So then you won't get confused with the gradient m naught. So this is m naught, the mass. So the gradient is m. So p over m naught c is a constant. So that's going to be the gradient. This is on the x-axis. This is the y-intercept point. So if you plot a graph of t against temp time in seconds, t in Kelvin or Celsius. If you plot a graph, it will be a straight line, but it won't pass through the origin because there is a y-intercept point. Find the gradient. So this is going to be ti. Find the gradient of the graph. So the gradient will be equal to p naught over mc. P over m naught c. So c, the specific capacity, will be equal to p over gradient times mass of the metal block. From that you can calculate the specific heat capacity of the metal block. Okay, so there could be questions like this based on this practical. If the metal block is not completely immersed in, if the heat is not completely immersed into the metal block, what will happen? So here we are taking all the power given out. Power means the heat per second, is it heat energy per second given out by the heater is transferred to the metal block. So that's the reason if I know the power of the heat already, if the catalog says the power output of the heater, means every second it will totally give out that much of power from all part of the heater. So the whole heat, all the part of the heater should be completely immersed into the metal block. Or if I don't know the power, I will calculate the input power, electrical input power, by using P equal VI. So efficiency is normally 100% because heater won't create any other type of energy other than heat. So the output power also VI. But if the metal block is, if the heater is not completely immersed into the metal block, say if the part of the heater is outside, something like this. If the part of the heater is outside, a significant amount of portion of the heater is outside the metal block, what will happen? Only a portion or fraction of the heat given out by the heater will be absorbed or accepted by the metal block. A certain amount of heat will be lost to surrounding from the part of the heater outside the metal block, is it? So here, when we are using this equation, what mistake or what error could happen means we assume all the heat is given to the metal block, but actually a portion or fraction of the heat given by the heater is transferred to the metal block. The balance is emitted to the surrounding because the small portion of the heater is outside the metal block. So there what happens, the temperature at a particular time, the temperature measured by using the thermometer is going to be lower than the expected value. Is it? The temperature that we are going to measure at a particular time will be lower than the expected value. This is true. This graph, assume this graph when there is no heat loss to surrounding. Okay, at a particular time t, the temperature measured is T. But here what's going to happen, at the same time T, when I do the practical, when a small portion of the heat is outside the metal block, the temperature I'm going to measure will be lower than the actual value that it should be obtained. But I'm going to get a lower value. So for the same time, the value of the temperature will be lower somewhere here. So like that, at all part, during every time, the measurement of the temperature, practically what we measure is going to be lower than the actual value. Actual value means when there is no heat loss to surrounding, the whole part of the heat is inside the metal block. So if you plot a graph now, the shape of the graph will be like this. It will be a straight line, but the gradient will be lower, because every time the temperature measurement is going to be lower than the actual value. So the graph will be something like this. You will have a graph, but that will have the same initial point Ti, that's the initial room temperature. The gradient of the graph will become smaller, so the calculated value through the experiment will have a larger specific capacity than the actual value. Okay, when a portion of the heat is outside the metal block, the specific capacity calculated by using the practical will be larger than the actual value, because gradient is going to be smaller. The gradient is going to be smaller than actual value. The slope will be less. Right, so there could be another thing. Now the heat is kept correctly, right? That means the all part of the heat is completely inside the metal block, like what I drew earlier. So the heat is kept correctly, completely inside, but the thermal insulation is not properly done. So there is heat loss to surrounding from the thermal insulation. So there what will happen? Okay, there's a chance due to the thermal insulation not properly done, the heat will be lost to surrounding. So at a particular temperature, the value what we expect will be lower than the actual temperature at a particular time, because there is heat loss to surrounding from the metal block. Also, what happens? The temperature of the metal block is increasing. When the temperature of the metal block increases, what will happen? The rate of heat loss to surrounding also will increase. The rate of heat loss to surrounding also will increase when the temperature increases. So initially the heat loss, the rate of heat loss from the metal, maybe for example, if the initial temperature is 25 degrees Celsius, at 35 degrees Celsius, the heat loss to surrounding, compared to that at 45 degrees Celsius, heat loss to surrounding will be more, because when the temperature of the metal block increases, rate of heat loss to surrounding also will increase. So when the rate of heat loss to the surrounding increases, rate of increase of temperature will decrease. Rate of increase of temperature will decrease. So there the graph will become like this, because when the temperature increases, rate of heat loss to surrounding will increase. So the rate of increase will decrease, means the graph will bend. So the graph will go, the temperature is increasing, but rate of increase is decreasing. So there will be a slight slope. It won't be a straight line. The graph will be a curve like this, shown on the blue color. The black color graph is the actual graph when there is no heat loss to surrounding, and also the thermal insulation is good and the heat is completely inside. You will get a straight line like this. But if the insulation is not properly done, the graph will be a curve like this. Okay, so the next practical is measuring the specific heat capacity of metal piece. So you are given identical coins, metal coins. How to find the specific capacity of the material of the coin? So there you can't keep a heater like what I explained earlier, metal block. So it's a coin. So there's no space for the heater to keep, even you can't keep a thermometer there. So what we do, the identical metal coins, 2 or 3 coins, you can heat it in water bath until the temperature. You should have a thermometer here also, until the thermometer reading in the water bath becomes 100 degrees Celsius, the boiling point. So it's a steady temperature, you know that boiling point. So you heat the metal pieces or the coins given in water bath until the water bath reaches 100 degrees Celsius. Keep it reasonably longer time, because the metal pieces should be in thermal equilibrium with the water bath. So now they are at 100 degrees Celsius, metal pieces. Then already you would have set up a calorimeter. You know, calorimeter is a small metal container with proper thermal insulation. You should know the specific capacity of the container of the calorimeter. Most is made of copper, so we know the specific capacity of the copper. You can get it from any book or anywhere. So this is a copper container. Some books they say, it's a calorimeter. Whatever it is, it's a calorimeter. No, mostly made of copper. So we should know the specific capacity of the copper. There must be a known mass of water. So there must be a known mass of water, the mass of the water mW at initial temperature. Mostly it is at room temperature. Let it be T1. So T1 is the initial temperature of the water. You must know the mass of the water. You must know the mass of the calorimeter container. Let it be MC. So the water is at room temperature, calorimeter container also at room temperature. So they will be in thermal equilibrium. They all are at room temperature T1. Both calorimeter and the water both are at temperature T1. Okay. It should have a proper thermal insulation. There must be a lid. That also should be thermally insulated. Now what we do, we take the metal piece out of boiling water and drain it quickly with blotting sheet and transfer it to the container where the water contains its calorimeter. So and stir it well by using a stirrer, stir the water well. You will see the temperature of the thermometer, temperature of the water or the thermometer reading will increase and it will reach a steady value. So what is happening now? The temperature of the water is T1, mostly room temperature, let it be 25 degrees Celsius, something like that. This is a boiling water, so the metal pieces are initially at thermal equilibrium with the water, so they will be at 100 degrees Celsius. Now when they are transferred to the water, you have to drain it and transfer by using blotting sheet. You can remove the water in it. Quickly you have to do that. And now what's happening? These metal pieces are at higher temperature. You must know their masses, total mass of the metal pieces. You must know that is mass of the metal piece. Let it be We should know that before putting them into the water. You would have measured it. Okay. Now when the metal pieces are transferred to the water, now there will be heat flow because the metal pieces are at higher temperature, 100 degrees Celsius. Water and the calorimeter, they both are at lower temperature, room temperature, maybe 25 or something like that. So I already told heat will flow from higher temperature to lower temperature. So the metal pieces are going to lose heat. What's happened to that heat lost by the metal pieces? Heat lost by the metal is a conservation of energy, nothing else, conservation of energy. Heat lost by the metal pieces will be gained by both water and calorimeter. So they all are in a closed environment. There is no heat loss to surrounding. So finally what happens? The metal piece is losing heat. Both water and calorimeter, they are in contact among them. They are gaining heat from the metal pieces, means their temperature will increase. Finally, the metal piece temperature is decreasing. Temperature of the both water and calorimeter increasing. They will reach a thermal equilibrium, steady state. That temperature must be recorded by using the thermometer. So you have to stir it continuously and record the thermometer reading until the thermometer reading comes to a stable value, steady value. So that is the final steady state temperature. So there I can write the equation: heat lost by metal piece is equal to heat gained by water plus heat gained by calorimeter. This energy equation you must be able to write. You must be able to identify which component is losing heat and which components are gaining heat. Total heat loss equal to total heat gain because no heat loss to surrounding. Okay, so the final temperature becomes, we have to record the final temperature. Let it be T, the final temperature. TF we will say final temperature, TF. So that will be the stable temperature or steady temperature recorded by the thermometer. So the temperature of the metal pieces, they were at 100 degrees Celsius. Now they are becoming TF. So they are losing the heat. They all are going to be in thermal equilibrium finally. So heat lost by the metal piece is equal to M Cm. We are going to find Cm, that's the aim of the experiment. So the change in temperature for the metal, they were at 100 degrees Celsius. Now they are at TF is equal to heat gained by water. Mass of the water we must know. Specific heat capacity of the water also we must know. And final temperature of the water Tf, they were at initially T1, room temperature. Same way, calorimeter, we must know the mass of the calorimeter container. We must know the specific capacity of the calorimeter, mostly it's copper, but I'll put Cc, the specific capacity of the calorimeter. So its temperature also increasing to Tf from T1. Okay, so here we know all the quantities. We know the mass of the metal. We are going to find this. This is an unknown. We know the final temperature recorded by thermometer. We know the mass of the water, specific capacity of the water we must know. Final temperature we measured. Initial temperature of the water we measured it, mostly room temperature. Mass of the calorimeter, specific capacity of the calorimeter we must know. Tf, T1, everything we know. Only Cm, specific capacity of the metal piece, is unknown. So everything know, only one unknown quantity you can calculate. We don't plot a graph, very difficult. So we can calculate the Cm from this equation. Then we can repeat this experiment. If you want, you can repeat this with different mass of water. Yeah. But mostly we start with the same room temperature, but you can change the mass of water to get different final temperatures. You can repeat this experiment several times and get for each, during each experiment, find the value of Cm, and Cm is a constant, it's for a given type of material. I told the specific capacity is constant. So finally find the mean value of Cm. That's a simple experiment. Always the change in temperature must be a positive quantity. If it is increasing, final temperature minus initial temperature, decreasing, initial minus final. So always we should keep energy positive everywhere. Okay, we'll discuss few exam style simple questions. This topic is nothing hard, very easy. O-level IGCSE also you had it, but questions compared to IGCSE, these questions might be a little harder, but actually they are not harder questions. Basically conservation of energy. Heat loss something equal to heat gained by something, that's all, right? Okay, you have to identify which component is losing heat, which components are gaining heat. Something like that you have to identify. Okay, so I wrote the question shortly. Thermally insulated copper coil. So it's a insulated copper coil. Okay, mass of the coil is given 30 grams. Heat coil, right? It's a thermally insulated heat copper coil, means it won't lose heat to surrounding. I didn't write that, but I'm reading it. Thermally insulated copper coil that has mass 30 gram and its resistance is 25 ohms. Thermally insulated copper coil, and a voltage of 5 volt is applied across the ends of the coil. So you know coil is going to get heat because there's a current flow through it. So temperature of the coil will increase, right? Specific heat capacity of copper is 380 joule per kilogram. Calculate temperature rise in 1 minute. That's the question. So here the coil is not heated, but the coil is heated by using electrical energy. So power of the input power in the form of electricity, electrical input power is going to be output heat. Okay, so we can say heat input power or input electrical energy equal to gain in heat is going to gain heat. It's thermal energy, or it's going to gain heat. Okay, so that means the atomic vibrations. It's like we are doing work by using electrical energy. So the atoms are going to vibrate. So the temperature is going to increase. That means temperature is increasing means heat is flown to the coil. That way we can take it, is it? So input electrical energy, power into time, is equal to mc delta T. So power is equal to P equal V squared over R. You know the voltage given, resistance given. So P is equal to V squared over R. P equal V squared over R. You learned that in unit 2. So instead of P we can write V squared over R into T is equal to mass of the coil, specific capacity of the coil into delta T. The question is delta T. Okay, V squared we know 5 squared over R is 25, 60 seconds because 1 minute. Mass of the coil is 30 grams, so we have to convert to kilogram. 30 into 10 to the power minus 3 into specific capacity 380 into delta T. We need to find it. Find the delta T. Simple question. .26 degrees Celsius or 5.26 Kelvin. Either way you can say, because I told change in temperature will have the same numerical value in both Celsius scale and Kelvin scale. Okay, so this is the second question. An electric kettle operates at 230 volt at a current of 8 amperes. So we can find the input electrical power P equal VI. So the output power in the form of heat also the same we take normally, because the efficiency of heating coil is 100%. It consists of 600 grams of water, and the temperature is increased from 15 degrees Celsius. The temperature of the water and the temperature of the kettle itself increased from 15 degrees Celsius. The specific heat capacity of water is given 4200, and kettle itself requires 350 joule for every 1 degree Celsius rising temperature. If the temperature of the kettle increases by 1 degree Celsius, the kettle material will absorb 350 joule. If it increases by 2 degrees Celsius, the kettle itself will absorb 700, 350 into 2, like that. For every temperature increase, the kettle will absorb heat. So if the temperature increase is delta T, the kettle will absorb heat which is equal to 350 into delta T. So here first we should identify the energy equation, because I told it's a conservation of energy. So it's like this: heat given out by heater, is equal to heat absorbed by the water plus heat absorbed by water, or heat gained by water, plus heat absorbed by kettle. Right, so when we consider that way, heat given out by heater means power of the heater P into time. Heat absorbed by water, mass of the water we know, MW, CW. The change in temperature, we'll put delta T, we'll substitute later, plus heat absorbed by kettle, every 1 degree Celsius 350 means 350 into delta T. Okay, so we substitute power, you know, P equal VI. So also we know, I put it here, P equal VI. I want to use that here. So instead of power, I can say VI. VI is 230 into current 8. The time is the question, T. Mass of the water 600 means 600 gram divided by 1000, or into 10 to the power minus 3. Specific capacity is given in 4200 joule per kilogram. So that's the reason I converted to kilogram. It should tally, the units should be the similar. So 4200 delta T 100 minus final temperature 100. Initially it was at 15 degrees Celsius. Yeah, 15 degrees Celsius. Plus 350 into 100 minus 15. Solid. The only unknown is T. Find the time. 132.6 seconds. Okay, so a car of mass, total mass of the car is given 900 kilograms, moving at a speed of 30 meters per second. So it consists of 4 wheels. Each wheel has a braking disc. A braking pad consists of a disc. Each disc has a mass of 2.8 kilogram. So when you apply the brake, the disc goes and grips the wheel and the car slows down. The question is, when the car is moving, stops from initial speed of 30 meters per second, what could be the increase in temperature of each disc? What assumption did you make in your calculation? That's the question. So here we assume when the brake is applied or when the brake pads grip the wheels, the drum of the wheels, sound also will be produced. The tires might grip on the road and heat will be produced on the tires also. So we assume all the initial kinetic energy of the car is converted to heat in 4 discs. That's the assumption we take. So what we are calculating is the possible maximum increase in temperature. So practically it could be lower because sound also will be produced. The sound is actually created from the part or fraction of the kinetic energy of the car. Tires might grip on the road and there could be increase in temperature of the outer surface of the tire. There could be increase in temperature of the road also. But we assume all the initial kinetic energy just before braking, the kinetic energy possessed by the car is converted into temperature of the brake pads in 4 wheels. That's the assumption we have to say, right? So by using that assumption, we can go to the calculation. Loss in kinetic energy of the car, heat gained by or heat increase in by 4 braking pads or braking discs. So loss in kinetic energy, half mass of the car is given 900 kilograms. Initially the temperature speed 30 minus 0, finally it comes to rest. So there are 4 wheels. So if I do it for one wheel, the heat absorbed by one disc is equal to mass of the disc. So MC delta T I'm going to use. Mass of the disc is given. If I want, I can write it in equation, then I'll go to the numerical value. So half m u squared minus half m v squared. That's a loss in kinetic energy. V is 0. Mass of the disc, specific capacity of the disc, delta T. That's a question. This is for one disc into 4. There are 4 discs absorbing the same heat lost by the car. So now we can say half. This m is mass of the car. This is the mass of the disc. So mass of the car we know 900 into 30 squared minus 0 equal. Mass of the disc is 2.8. Specific capacity of the disc is given somewhere 460 into delta T is the question into 4 wheels. So find the delta T. That's the only unknown. Find the delta T. You will get 78.6 degrees Celsius or 78.6 Kelvin. Change in temperature is same in both units. Okay, so this is the 4th question. Metal piece of mass 0.2 kilogram at 100 degrees Celsius is dropped into 0.08 kilogram of water at 15 degrees Celsius. Water is contained in a calorimeter of mass 0.12 kilogram. Specific capacity of calorimeter 400. That's a calorimeter means there's a small container cup like that. It's a calorimeter container, that is 400 joule per kilogram per Kelvin. After dropping the metal piece, water achieves a steady temperature because metal piece is going to lose heat. Both water and calorimeter container, they are going to gain heat. So the final temperature, the steady temperature becomes 35 degrees Celsius. So all 3 components, that is the metal piece, water and calorimeter, all will be at the same temperature finally 35 degrees Celsius. water specific capacity. You will find the specific heat capacity of the calorimeter metal piece. Okay, so nothing I told already. It's a conservation of energy. You should be able to identify which component is losing heat and which component or components are gaining heat. So here we know that the metal was initially at higher temperature, 100 degrees Celsius. So heat flows from, heat is the flow of energy due to temperature difference. So since the metal piece is at 100 degrees Celsius, heat will flow from metal piece to water and calorimeter. Right, so we can say heat lost by metal piece equal heat gained by lost by metal piece equal heat gained by water plus heat gained by calorimeter. Okay, we'll write this in symbol. So heat lost by metal piece, mass of the metal piece, we'll say cm. That's we are going to find it. Initial temperature was 100 degrees Celsius. Finally, the temperature becomes 45 degrees Celsius. Finally the temperature becomes 35 degrees Celsius. We'll substitute it, but I'll put the temperature change. Heat gained by water, mass of water, specific heat capacity of water. Water was initially at 15 degrees Celsius and finally the temperature becomes 35. So 35 minus 15. For calorimeter, mass of the calorimeter container is 0.12 kilogram. MC, I'll substitute later. MC cc, then that also 35 minus 15, because initially both water and calorimeter, they will be in thermal equilibrium. Okay, so then we'll substitute mass of the metal piece is 0.12 calorimeter of mass, 0.2 kilogram mass of the metal piece, 0.2 kilogram. So 0.2, that's a mass of metal piece. Specific capacity of metal piece, we need to find it into 100 minus 35, that is 65. Is it mass of the metal piece? 0.2. We need to find the specific capacity of the metal piece. 100 minus 35 is the change in temperature, that is 65. So mass of water 0.08. 0.08 is the mass of water. Specific capacity of water given 4200 into this also, 35 minus 15, that's going to be 20. Now mass of calorimeter, that is given as 0.12. Mass of calorimeter of mass 0.12. Specific capacity of the calorimeter 400 into this is 20. So since we know everything except cm, solve it, find the cm. That's a specific capacity of the metal piece. So you will get 590.8 or 591 joule per kilogram per Kelvin or per Celsius. Okay, so fifth question, 250 gram of oil at 100 degrees Celsius is quickly mixed up with 750 gram of same type of oil at 30 degrees Celsius. By assuming the heat loss, by assuming that the heat absorbed by the container is negligible, find the final steady temperature of the oil. So here anyway we assume there is no heat loss to surrounding, right? That's the way, otherwise we can't do this type of calculations, because even my previous question they could ask in the past papers, they asked after calculation what assumption you made in the previous calculation. Answer: there is no heat loss to surrounding. Otherwise you can't do this type of question, because we are dealing with conservation of heat energy. Okay, so here there are same type of oil in two different container, different mass, but container, the amount of heat that could be absorbed is negligible. One oil is higher temperature, which is at 100 degrees Celsius. The next oil, which is the same type, 750 gram, is at a temperature of 30 degrees Celsius. So when you mix it, both oil, same type of oil are going to be the same oil. What could be the final temperature? That's a question. Here also, simple. So we don't need to consider anything heat absorbed by the container. So just the heat transfer is going to happen between the hot oil or the warm oil and the cold oil. So heat lost by warm oil or hot oil is equal to heat gained by cold oil. That's all. So finally, both oil, after they mixed, they are going to be at the same temperature. That's the question. We are going to find it. Okay, so here we can say heat lost by hot oil equal to heat gained by cold oil. Cold means which is at lower temperature, 30 degrees Celsius. Not cold means, I mean compared to this is cold. Yeah. So the specific capacity is the same. So I told that it's depending on the type of the material, regardless of mass, regardless of temperature. So both are same type of oil, so they'll have the same specific heat capacity. Heat absorbed by the container is negligible. So the mass lost by hot oil, so I say mH, H stands for hot, specific capacity is the same. So the final temperature is the question. It's going to lose the temperature from 100 degrees Celsius to final temperature T. The cold oil, I'll say MC, C stands for cold oil, same specific capacity, but its temperature is going to increase to T from 30. That's all. Substitute C and C will get cancelled. Specific capacity is not given, they will get cancelled in this equation. So mass of the hot oil is going to be that is 250 gram. We can keep it in gram, but we'll put it in kilograms, 0.25, because even if I keep it in gram, the units both sides will get cancelled, but I'll convert it to kilograms. 0.25 into 100 minus T is equal to mass of the cold oil, 750 means 0.750 into T minus 30. Okay, both sides there are T. Solve it, that is 0.25 into 100, that is going to be 25. Minus 0.25 T equal to 0.75 T minus 30 into 0.750. Solve it. T, you know how to solve it, simple algebra. So solve it, you will get the final temperature 47.5 degrees Celsius. So you can ask me, how do I know the final temperature in Celsius? Because initial temperature is in Celsius. Initially the temperatures are 130, they are in Celsius, so the final temperature should be in Celsius. Okay, it's a Edexcel IAL past paper question. The year I can't remember. An electric heater of power 6.2 kilowatts is used to heat the water in a shower. Water enters the shower at a temperature of 18 degrees Celsius and the flow rate is adjusted to 0.075 kilogram per second. So the amount of flow is continuously flowing through the heater. So specific capacity of water is 4200 joule per kilogram per Kelvin. So if you think like this question is given in terms of flow rate. So we don't have the mass of water heated and they are given the power of the heater, but how long it's heating, it's not given. So it's like something like this. So through the heater, if I imagine the heater something like this, water is entering through this one, water is entering through this one, it gets heat and leaves through this one. So we know the rate at which it enters. Every second what mass is entering 0.075 kilogram. Every second the mass of water leaving should be 0.075 kilogram because water cannot accumulate inside the heater. We assume like that. So here the energy equation generally for the water flowing through the heater. For the water flowing through the heater, if I write E equal mc delta T, that's a standard equation we write, is the energy equal to heat supplied or absorbed by water equal to mass of water. But here we don't know how long it takes to flow through the heater. So what we do, we know the power, divide the whole equation by time. So energy, that is heat supplied divided by time, is the power, output power of the heater. Mass per unit time, that is the rate of flow of mass. I divide the whole equation by time. So energy divided by time is the power of the heater, or power of the heater means that's the heat at which it supplies, output power of the heater. This is the rate of flow of mass, C delta T. Okay, so now we know the power of the heater, that's the output power of the heater, that is given as 6.2 kilowatt, 6.2 into 1000. So here this is M over T, that is rate of flow of mass, 0.075, 4200 specific capacity. Delta T, we need to find the final temperature. It enters at a temperature of 18 degrees Celsius. Solve it, find the T, you will get 37.7 degrees Celsius. Okay, so the next topic is latent heat. Okay, so when I start this lesson, I told that whenever there is a change in temperature of a substance, that means the average kinetic energy of the particles is changing, or whenever there is a change in average kinetic energy of the particles, there will be change in temperature. Okay, same way, whenever there is a change in potential energy, when that happens, change in potential energy happens only during state change. Whenever a material or substance or matter in a specific state, for example, when it is in solid state, so the average potential energy will remain constant. The potential energy, the average potential energy changes only during state change. For example, when a solid becomes liquid, that means fusion, that means when ice becomes water. So there you know when a substance in the solid format, solid state, the atoms or molecules are tightly bonded. So to become liquid, the bond should be weakened. So you should break the bonds, not completely. It should be the bonds should become weaker. So there the heat will be absorbed. Heat will be absorbed to break the or get the bonds weaker. So when heat is applied, what happens during the state change? When heat is applied, that state change will happen. One more thing I have to tell you. The state change happens normally at a specific temperature. For example, the ice becomes water at melting point, normally at 1 atm pressure, that is 0 degrees Celsius. Only at that temperature, ice will become water. Ice will melt at 0 degrees Celsius. So when the ice is at negative temperature, minus 10 degrees Celsius or minus 15 degrees Celsius, if you supply heat to the ice from a heater or when a source with higher temperature, if heat flows to ice which is at negative temperature, and if the heat flows evenly, what happens? The temperature of the ice will increase from negative temperature. For example, if the ice was initially at minus 15 degrees Celsius, so if heat flows from some other heat source which is at higher temperature to ice, and if the heat is supplied evenly, uniformly to the all part, what happens? The ice temperature of the ice will increase from minus 15 to 0 degrees Celsius. So there we need to consider the change in average kinetic energy of the molecules or particles of the ice. So their average kinetic energy will increase when the temperature of the ice increases from minus 15 or negative 15 degrees Celsius to 0 degrees Celsius. But when it reaches the 0 degrees Celsius, what happens? If you continuously supply heat in the same way evenly, all the heat you are supplying will be used to weaken the bonds. So at 0 degrees Celsius, the ice will start to melt until the whole ice melts. If the heat is supplied evenly, uniformly, until the whole ice completely melts, the temperature of the ice-water mixture. What do you mean by ice-water mixture? Means a part of the ice is already melted, so water is created. Now the water and ice both are there. So imagine a container something like this, a container which consists of initially just a piece of ice which is at minus 15 degrees Celsius. So you are heating it evenly by using water bath or something. You are heating it evenly, uniformly. So heat is supplied to it evenly. So what happened? The ice will melt. Now until the temperature of the ice becomes 0 degrees Celsius, the ice will remain as ice in the form of ice, solid format. When it reaches the 0 degrees Celsius, it will start to melt. So when it melts, a part of the ice would have melted already. So there will be water also. If the heat is supplied evenly, the water will remain at 0 degrees Celsius. Very important. The ice-water mixture will remain at 0 degrees Celsius until the whole ice melts completely. If you supply the heat evenly, uniformly, you should supply the heat. So until the whole ice or the completely ice melts, the ice-water mixture will remain at 0 degrees Celsius. So what happens to the heat we supply? All the heat we supply will be used to weaken the bond. The heat, that means weaken the bond means what happens? The potential energy will increase because we are giving heat. So the molecules are, the intermolecular force is getting weaker. So the potential energy will increase because the bonds are weakened, means the work is done to weaken the bonds. So that means the potential energy will increase. So there why we call this heat what we supply as latent heat. You know the meaning of latent means hidden means. So that means we are supplying heat, but there is no change in temperature. It remains at 0 degrees Celsius. From here to when the temperature becomes 0 degrees Celsius, it started melting. Initially, the temperature of the ice increased from minus 15 to 0 degrees Celsius. Still, we are supplying heat, but there is no change in temperature. It remains 0 degrees Celsius until the whole ice melts. We are supplying heat, so it looks like the heat we supplied is not detected or it's hidden because the reason all the heat we supplied is used to weaken the bonds. That's the reason that heat which is absorbed by the substance or absorbed by the ice during its state change from solid to liquid, that heat absorbed is called latent heat. The meaning of latent, it's like a hidden heat because no change in temperature. Right. Now then when the whole ice is melted, it will reach a state water at 0 degrees Celsius. Water at 0 degrees Celsius. Now when you supply the heat continuously, what will happen? The temperature of the water will increase from 0 degrees Celsius to 100 degrees Celsius. Now you supply the heat continuously, even when after it reaches 100 degrees Celsius. What will happen? The water will start to boil. The water will start to boil and it will become vapor. So there, the temperature will remain again 100 degrees Celsius. So here also again the latent heat. You are supplying heat when the water just reaches 100 degrees Celsius. Even after that, when you supply the heat, the temperature of the water has no change. That means the heat you are supplying is used to break the bonds. Earlier, solid to liquid, the heat we supplied is used to weaken the bond. Here, it is completely breaking the bond. So the liquid becomes vapor and the vapor will escape out of the container. So here also it is latent heat. So this happens at a specific temperature at 1 atm pressure, that is called boiling point. So the solid becomes liquid at a temperature called melting point. Liquid becomes vapor at a temperature called boiling point. So during the state change, all the heat supply will be used to change the potential energy. When solid becomes liquid, the potential energy will increase. There is no change in temperature. Careful, there is no change in temperature. That's the reason the heat supplied or absorbed by the substance is called latent heat. Same way, the liquid becomes vapor at boiling point. During boiling, also there is no change in temperature. All the heat supply will be absorbed to break the bonds to escape completely as vapor. That happens for water at 100 degrees Celsius. That also latent heat. So state change occurs only during certain temperatures, certain specific temperatures that normally depends on pressure also, but we don't consider much in your syllabus. But anyway, but you must know for any matter, the state change occurs at a specific temperature. The temperature at which solid becomes liquid is called melting point. Liquid becomes vapor is called boiling point. Same way, when liquid becomes solid is called freezing point. Mostly, I think, yeah, for most of the substances, the melting point and the freezing point are almost the same. But water is, we know that water becomes ice at 0 degrees Celsius. Ice becomes water at 0 degrees Celsius. For most of the substances, the melting point and the freezing point are the same. During freezing also, when water becomes solid, it happens at 0 degrees Celsius. So the temperature of the water could be initially at, for example, room temperature, 30 degrees Celsius. When you keep it in a freezer, the temperature of the water will decrease if the heat is absorbed from the water evenly. When the water reaches 0 degrees Celsius, until the whole water becomes solid. That means until the whole water in the container becomes solid, it will remain at the freezing point. After it becomes solid, then the temperature of the water will decrease below 0 degrees Celsius and it will become negative temperature. Okay, so for that the heat should be absorbed evenly from the water. Okay, specific latent heat of fusion, that means minimum amount of heat required to convert a unit mass of solid into liquid at its melting point. That word must be there. At its melting point is defined or is called specific latent heat of fusion. Again, minimum amount of heat required to convert 1 kilogram, or you can say minimum amount of heat required to convert a unit mass of solid into liquid at its melting point is defined as specific latent heat of fusion. So if I put it in words, specific latent heat of fusion equal to amount of heat required or heat transferred over mass of state change, mass which becomes solid to liquid, mass of state change. Normally this is denoted by fusion, so LF, latent heat of fusion. Most of the books they use LF. Some books they use L for both specific latent heat of fusion and specific latent heat of vaporization. Same notation. Some books they use LF. I use LF. Heat transfer, that we can put E over delta M. That's the mass of solid becomes liquid at its melting point. So if you cross multiply, E equal LF into delta M. So the unit of LF is joule per kilogram or joule per gram, whatever it is, we can use it, no problem. So this is the amount of heat transferred. That means when solid becomes liquid, when delta M is the mass of solid converted to liquid, means this amount of heat will be absorbed. Same way, the same mass of liquid becomes solid, this amount of energy will be, that means this amount of heat will be released. Either way, this is true. That means when delta M mass of solid becomes liquid, this amount of heat will be absorbed. Same way, when a mass delta M of liquid becomes solid, this amount of heat will be released. Either way, that is correct. Okay, so next thing is specific latent heat of vaporization. What does it mean? Minimum amount of heat required to convert a unit mass of liquid into vapor at its boiling point. The word boiling point must be there. Minimum amount of heat required to convert a unit mass of liquid into vapor at its boiling point is defined or called specific latent heat of vaporization. So the format of the equation is same as fusion and vaporization, same. So heat transfer or mass of state change. So the mass of state change from liquid to vapor. So here we use LV for vaporization. E is the heat absorbed. Delta M is the mass of liquid becomes vapor. So the equation is the same format. Here also, when a mass delta M of liquid becomes vapor at its boiling point, the heat absorbed is equal to LV into delta M. Same way, when delta M is the mass of vapor that becomes its condensed into water at 100 degrees Celsius or at its boiling point, at the point at which condensation happened, is the same for most of the substances. So when a mass delta M becomes liquid from vapor, then the heat that is released is also the same amount. Okay, so this is a simple experiment to measure the specific latent heat of fusion of ice. So there are two identical funnels. They consist of same mass of crushed ice at 0 degrees Celsius. So it's a melting ice. That means 0 degrees Celsius. The ice will melt at 0 degrees Celsius. Until that, the temperature of the ice will decrease from, I told already, -20 to 0. Until that, ice won't melt. At 0 degrees Celsius only, the ice will melt, because that is the melting point of ice. Any substance, it melts at its melting point. Okay, so different substances have different melting points, right? Okay, two identical funnels consist of same mass of crushed ice, but this funnel consists of heater. We should know the power output of the heater. This does not have any heater. So in both funnels, the ice will melt. So we should complete the setup and switch on a stopwatch. After a known time t, we should measure the mass of water collected in both containers. So here the water is collected due to ice melted due to the environment, the temperature flowing from the surrounding. So the funnels are not thermally insulated, so the ice will get heat from the due to the room temperature. Here the ice is the water collected here is due to both ice melted due to the room temperature and due to the heater. So here the mass of water collected will be more in second diagram compared to the first diagram. So if I say the mass collected here is M2 and here the mass collected of water is M1. So M2 minus M1 is the mass of water due to heater. So the heater also melts ice. So the M2 minus M1 is the amount of ice melted due to heater. Okay, so we know the power of the heater. We know this practical, how long we allowed water, ice to melt. So we know the time, which is T. So here we can say the energy equal to delta M into LF Energy is the power of the heater and how long it was switched on, we know that. The delta M is M2 minus M1 into LF. From this we can find the latent heat of fusion by using this equation. So repeat this experiment and find the mean value. You will get the specific latent heat of fusion of the ice. Okay, so what's the difference between boiling and vaporization? Vaporization means, for example, when you wash your clothes and put it, it'll get dry, is it? So there the water in the cloth vaporizes. So there it won't reach the 100 degrees Celsius. Even at room temperature, water can vaporize. So the difference between boiling and vaporization you must know, because what we learned, specific latent heat of vaporization, even we call the word specific latent heat of vaporization we call, but that equation what we learned is correct only at boiling point. So what's the difference between boiling and vaporization? First difference you must know, boiling occurs only at a specific temperature called boiling point. For water 100 degrees Celsius, different substances that boiling point could be different. Vaporization occurs at any temperature, even at room temperature 20 degrees Celsius. If you mop the floor tiles, it will get dry after a few minutes. So its vaporization is occurring. So vaporization occurs at any temperature. Boiling occurs only at boiling point. So the equations what we learned related to specific latent heat of vaporization is applicable only during boiling point. Okay, that's the first difference between boiling point and vaporization. The second one, the difference between boiling and vaporization. During boiling, bubbles will be formed. But during vaporization, bubbles won't be formed. Might, I don't know, but mostly bubbles won't be formed during vaporization. Less chance. Mostly no. But boiling means bubbles will be formed. Third important difference, vaporization occurs only on the surface of the liquid. Vaporization occurs only on the surface of the liquid, but boiling occurs in all parts of the liquid. Boiling occurs at all parts of the liquid. So these are the three differences you must know. Okay, so we'll do few exam style questions related to latent heat. Specific latent heat of vaporization of water is 2.25 megajoule per kilogram. Calculate the energy required to change 16 grams of boiling water. So that means it's already at boiling point. 16 grams of boiling water into steam. So that's very simple. So E equal L times delta M. So L we do the latent heat 2.25, vaporization LB we can put 2.25 into 10 to the power 6 megajoule. Delta M 16 grams, 16 into 10 to the power minus 3 joules. Solve it, you'll get the answer 36,000 joules. That's the answer for first part. Okay, so this is the amount of heat required. Second part, during another experiment, an electrical heater decreases the mass of boiling water in an insulated container by 16 grams during 1 minute. So the heat required to vaporize 16 grams is the same thing. So power of the heat, if I say P into T is the energy what we calculated, power into the time is 60 seconds, 1 minute, during 1 minute. So energy is 36,000. So power of the heater is 600 watts. Okay, so second question, an electric kettle operates at a potential difference of 230 volt and a current of 8 ampere. So by using it we can find the power output of the coil of the heater. So P equal VI. It contains 600 gram of water at boiling point. So it has reached 100 degrees Celsius. So if you supply heat continuously, it will vaporize. The water will boil and vaporize. Automatic cutoff of the kettle fails to function. The kettle is manually turned off 3 minutes after the water began to boil. How much water will be left in the kettle? Specific rate of vaporization of water is given. So nothing actually. Here we'll find, we'll use the equation, the same thing. Energy required to vaporize the water is equal to LV into delta M. So energy means power into time. We know that energy is equal to power into time. So power means VIT. So that we'll substitute here. So the voltage is 230. Current is 8 amperes. And the time 3 minutes. So 3 into 60. So I am going to calculate what mass of water will boil and vaporize. Boil and vaporize. I want to find it. So LV we know, latent rate of vaporization, given 2.25 10 to the power 6. The value could be different sometimes books because depending on the impurity, anyway whatever it is. So 2.25 10 to the power 6 into delta M. We'll find the mass of water boiled and vaporized. So delta M you'll get 0.147 kilogram. That means in grams, 147 gram will be vaporized. So the question is, how much water will left in the kettle? So water left in the kettle, initially 600 grams. Now 147 grams already vaporized. So the balance will be 453 gram. Okay, so the third question, an electric kettle which does not switch off itself contains 700 grams of water at 30 degrees Celsius. Power of the coil of the kettle is 10 kilowatts. Specific heat capacity of the water is 4200 joule per kilogram per Kelvin. The kettle itself requires 400 joule for every 1 degree Celsius rise in temperature. That's called heat capacity, not specific heat capacity, heat capacity. But that word is not much used in your syllabus. 400 joule for every 1 degree Celsius rise in temperature. Specific rate of vaporization of water 2.25. Find the minimum time required for the kettle to boil dry. That means you need to completely vaporize all 700 grams of water, fully vaporize. What's the minimum time required? So anyway, if it wants to boil and dry, fully vaporize, first the temperature of the water should reach 100 degrees Celsius boiling point. So when the temperature of the water reaches 100 degrees Celsius, temperature of the kettle also will reach 100 degrees Celsius, because always water and the kettle will be in thermal equilibrium among them. So the equation that we can write is energy, total energy required is equal to, first we need to bring the temperature of the water to 100 degrees Celsius, M water MC delta theta, M water CW, delta T will be 100 minus 30. Then the temperature of the kettle also should increase. That will take every 1 degree Celsius rise, it's going to take 400 joules. So 400 into delta T, that is 100 minus 30. Then what's going to happen? We are going to vaporize all the water, that is LV into delta M. So delta M is 700 grams. So this is the total amount of energy required. So energy is equal to power into time. So we know the power, that is 10 kilowatts. So 10 into 1000 into T. This is the power. P into T, P 10,000. Mass of water 700 gram means 0.7 into 4200 into 100 minus 30, that is 70, plus 400 into 70 plus latent heat of vaporization 2.25 10 to the power 6 into delta M. We are going to vaporize all the water completely, so 0.7. So find the T. So that will be 181 seconds. So here we assume no heat loss to surrounding. The kettle is thermally insulated. We assume like that. That could be an question like what's the assumption you made in this calculation? There is no heat loss from the kettle to the surrounding. So we are using actually the conservation of energy given by the heater coil, how it transferred to other components, water, kettle, then water to vaporize. Okay, so this fourth question in latent heat says that 0.02 kilogram of ice and 0.1 kilogram of water are in a container. So that means there's ice water mixture that will be at 0 degrees Celsius. Steam at 100 degrees Celsius pass through water ice mixture until all the ice is just melted. So even after ice melt, the temperature of ice water mixture will be 0 degrees Celsius because they say just melted. How much water is now in the container? Finally, how much of water will be there? Because already 0.1 kilogram of water there, we know that. Now 0.02 kilogram of ice is going to melt, means there will be extra 20 grams because 0.02 kilogram is equal to 20 grams. So 0.1 kilogram, with that this ice should be added, or 0.12 kilogram is going to be there. Is it 0.12 kilogram of water is going to be there, but there will be more water because what's happening, the steam at 100 degrees Celsius is the agent that's going to melt the ice. So when 100 degrees Celsius steam passes through ice water mixture, what happens when 100 degrees Celsius steam passes through ice water mixture? First, the steam will condense and become water at 100 degrees Celsius. When steam condenses, immediately there's a latent heat of we don't say latent heat of vaporization is there, we don't say latent heat of condensation, but vaporization and condensation happens at 100 degrees Celsius. So when 100 degrees Celsius steam becomes water, it will be at 100 degrees Celsius water immediately. So there the steam is going to lose heat during condensation. Then what's going to happen? The water which is produced during condensation, which is at 100 degrees Celsius, is going to lose its heat further to melt the ice until the temperature of this condensed water becomes 0 degrees Celsius. Is it? So there are two different processes going to happen during steam passes through ice water mixture, because the ice water mixture is just melted, means finally we have water at 0 degrees Celsius. So when 100 degrees Celsius steam passes through ice water mixture, first it will condense into water at 100 degrees Celsius. Then the water which is at 100 degrees Celsius, which is obtained from the condensation of steam, that water which is at 100 degrees Celsius will lose its heat further and melt ice until that temperature of the water becomes 0 degrees Celsius. So here we can write the energy equation like this. Heat lost by vapor or steam during condensation So during this process, the steam is going to lose heat and it will become water at 100 degrees Celsius. Now there is water at 100 degrees Celsius. What mass of steam condensed? We don't know. We are going to find that. Now the water which is obtained due to condensation will be at 100 degrees Celsius. But finally we have water, ice water mixture at 0 degrees Celsius, because they are saying ice is just melted. Means finally all will be at 0 degrees Celsius. So then we can say heat lost by the water that means water obtained during condensation So heat lost by the water which is obtained during condensation. The heat lost by the water which is obtained. So you can say which is obtained during condensation. So that water because when there is steam which is at 100 degrees Celsius steam, when it condenses, first it will become 100 degrees Celsius water. So that water can't stay inside. If that water stays inside ice water mixture, this water will lose its heat and melt ice further. Finally they are getting finally they are getting water at 0 degrees Celsius. So this water which is obtained during condensation also going to lose heat further. Finally, the heat lost during these two processes will be used to melt ice, just ice. Which ice? 0.02 kilogram of ice. Heat absorbed by ice during melting. Okay, so heat lost by steam means the mass of steam contents we don't know. We'll put delta M times LV. The condensation is same as vaporization. So the same mass of steam now has become water at 100 degrees Celsius. So its temperature is going to decrease to 0 degrees Celsius. So I'm going to use MC delta theta. Instead of M, I'm going to be delta M CW delta T. So the delta T is 100 minus 0. Now that's going to be the mass of ice, delta M ice, we know that is 0.02 into L fusion. Okay, so the mass of vapor condensed we don't know, we'll find it. So that's delta M into latent heat of vaporization is given here 2.3. Earlier we used 2.25. Anyway, 2.3 megajoule, 2.3 10 to the power 6 plus delta M, the same water which is obtained during condensation, time 4200 into delta T, 100 minus 0. So the mass of ice which is melted, that is 0.02 kilogram. Latent heat of fusion, that is 3.4 10 to the power 5. From this, only one unknown, find the delta M. So delta M, that will be 2.5 10 to the power minus 3 kilogram. 2.5 10 to the power minus 3 kilogram. That is 0.0025 kilogram. 0.0025 kilogram. So this is the mass of vapor condensed. Okay, so the question is, what will be the final total mass of water? So the question is, how much water is now in the container? So total mass of water finally. The water which is obtained during condensation, that is 0.0025 kilogram. Then already the ice is melted, so 0.02 kilogram. And already there is water which is 0.1 kilogram. And all of them, you will get the final answer. So that's going to 0.1225 kilogram. Okay, so the next topic is gases. When we consider gases, in physics we consider two different types of gases. What are they? Two different types of gases we consider. The first type is called real gas. The other one is called ideal gas. Okay, what is real gas? Real gas means that exists in environment or that could be created in the laboratory. Something like oxygen, hydrogen, helium, argon, carbon dioxide. These all are real gases. When we consider real gases, they'll have intermolecular force. It depends on the volume. When we compress the gas and when the gas particles get closer to each other, the intermolecular force could increase. When the gas particles are far apart from each other, then the intermolecular force could be negligible. So the real gas has intermolecular force, therefore the gas could be liquefied. You know, when the temperature is decreased, already we learned that when the temperature increases, average kinetic energy of the particles, it would be liquid or gas or solid. When the temperature increases, the average kinetic energy of the particles or molecules will increase. Same way when you reduce the temperature, when you decrease the temperature, the average kinetic energy of the particles will decrease. And also when you compress the gas, by applying pressure or by when you compress the gas particles will get closer to each other, so they will form strong bond among them. So when they form a strong bond among them, the gas could become liquid. So that is the property of real gases. Generally, almost all the real gases could be liquefied, but the required pressure and temperature to liquefy a gas depends on the property of the gas and its type. But when you consider ideal gas, what is ideal gas? Means there is no such gas exists. It's a theoretical model of gas. So we take certain assumptions about ideal gases. Mainly, first assumption what we take is ideal gas does not have intermolecular force. Since ideal gas has no intermolecular force, means the ideal gas never becomes liquid. That means ideal gas cannot be liquefied. The real gas could be liquefied. The required temperature and pressure. The temperature has to be reduced below a certain value, that is called critical temperature. The critical temperature for different type of gases is different. For example, oxygen, the critical temperature is not much. Actually, it's almost even at the room temperature, oxygen could be liquefied by applying sufficient pressure. Even a petroleum gas could be liquefied even at room temperature by having a sufficient pressure. But not all gases could be liquefied at room temperature. They need different different amount of temperature and pressure. But anyway, almost all real gases could be liquefied. Ideal gases cannot be liquefied because they don't have intermolecular force. That is the main assumption we take. It's a theoretical model of gas. There is no such ideal gas exists. You can't find ideal gas anywhere. It's a theoretical model of gas because by having such simple modification of gas particles, we are able to develop theory based on statistics, and by using simple Newtonian mechanics, we can develop certain equations. Now, when we apply or use those equations for real gas, only thing we need to do corrections for the intermolecular force. We call Van der Waals correction. But anyway, those are not in your syllabus. So, for the theoretical reason, or to develop the theoretical models, we assume a gas called ideal gas. The main assumption that it does not have any intermolecular force, so therefore it cannot be liquefied at all. It will be always in the state of gas. It never becomes liquid, the ideal gas, but there is no such gas. Okay, so there are more assumptions about ideal gases. We better to know that. First assumption, it has no intermolecular force. Then we assume the ideal gases are rigid, tiny particles. Their volume, the gas volume of the gas is negligible. Then all the ideal gases, when they collide, the collision is perfectly elastic. The collision of ideal gases are always perfectly elastic, means the kinetic energy will be conserved during collision. Then we assume compared to volume occupied by the gas, volume of the gas particle is negligible. Then during collision, the contact time is negligible compared to time between two adjacent collisions. That is actually that idea or that assumption is taken to develop certain equations. For example, when you consider three gas particles, a gas particle X moves towards Y, it collides with the Y, then X is moving towards Z. First X is moving towards Y, collides with Y, then X is moving towards Z and colliding with Z. So during the collision, X and Y are in contact. So there is a contact time. Then after that, X is moving towards Z and colliding. So the time interval between this collision and this collision, there is a time interval. Compared to that time interval, the contact time during collision of X and Y is negligible. That one of the assumption. Then the next assumption is ideal gases could be compressed a lot. Any amount we can compress. That is one of the assumptions we take. They never becomes liquid. So and the last assumption, ideal gas motion of ideal gas is always random. That also you must know about the assumptions about ideal gases. So in the exam, if they ask what is ideal gas, you can say it's a theoretical model of gas which never becomes liquid, or theoretical model of gas. It cannot be liquefied since it does not have intermolecular force. Is the answer you should give when they ask what is ideal gas. A theoretical model of gas which does not have intermolecular force, and it will be always in the gaseous state. It never becomes liquid is the ideal gas. So when we consider the internal energy of real gas, the internal energy of the real gas is due to both kinetic energy and potential energy, because real gases, they have intermolecular force. But when we consider internal energy of ideal gas, that is only due to kinetic energy, because the ideal gas does not have intermolecular force. That means ideal gas has no potential energy. So the internal energy of the ideal gas is only due to kinetic energy, and it does not have potential energy. So when we consider a certain amount of gas in a closed container at a particular temperature, all the gases, but one more thing you should know, even real gases, they behave up to a certain extent, they behave as ideal gases when the temperature is high and the pressure is less. Because when the temperature becomes high means the particles and the temperatures become high, and when the volume is high or less pressure means the gas particles will be further apart. So the intermolecular force could be little bit negligible, so they can show more closer to ideal gas behavior. But when we consider internal energy of gas, mainly we think about real ideal gas, the internal energy is only due to kinetic energy. Even if we say that way, all the gas particles won't have the same magnitude of kinetic energy at an instant or at a particular temperature. Different gas particles will have different amount of kinetic energy because they are moving randomly, and they will have collision among them. So when you have certain amount of certain moles of gas in a closed container at a particular temperature, they all won't have the same magnitude of kinetic energy at an instant. They will have different magnitude of kinetic energies at an instant at a particular temperature. But we can consider the average kinetic energy of the gas particles. We are going to learn that. The distribution of the kinetic energy among the gas particles is given by Maqxwell-Boltzman distribution. There's an equation for that distribution of the probability, but we don't go in detail about that. Only thing you better to know the graph, the distribution curve is enough, and if you can interpret the curve in words, that is enough for your A level. Okay, so this is the Maqxwell-Boltzman distribution curve. It could be drawn number of particles against speed or kinetic energy. So the graph starts from origin. That means there is no particle, number of particles 0, and there is no particle with 0 kinetic energy. 0, 0 origin means there is no particles with 0 kinetic energy. Then you can see that this is the average kinetic energy. So the most of the particles, you can see the peak is here. Most of the particles possess the average kinetic energy, because different gas particles will have different kinetic energy at a particular temperature, but most of the particles will have the mean kinetic energy or average kinetic energy. Few or less number of particles can have lower kinetic energy, and few amount of particles or certain number of particles have higher kinetic energy. The graph becomes asymptote. That means there is no upper limit for the kinetic energy in the classical model. So that means very few, you can see the number, the height, the number, there's a y-axis. Only very little number or very few particles can have very high kinetic energy. That's the meaning of this distribution. When the this is at a particular temperature, so this is the range of the kinetic energy. When you increase the temperature, the height will become lower and it will become more wider. That means when the temperature increases, the number of particles having the average kinetic energy will decrease, but the range of the kinetic energy of the particles will increase. That's the reason the graph will become wider and shorter when the temperature increases. The Maqxwell-Boltzman distribution curve is more suitable for gases. Solids we don't draw because that's larger intermolecular force, potential energy. So the motion is not free to move. And also for liquid also we don't draw. Actually the Maqxwell-Boltzman distribution curve is more suitable for gases. Okay, so different gas particles will have different kinetic energy. So in a closed container, if there are certain number of gas particles, for example, there are n number of gas molecules or gas particles, and the closed container is at a temperature, absolute temperature we call absolute temperature, means temperature in Kelvin scale is called absolute temperature. So if it is at absolute temperature T, then the average kinetic energy of a gas particle is given by average kinetic energy of a gas particle is given by 3/2 kT. We can derive this equation from Maqxwell-Boltzman distribution. That probability equation we can derive it, but anyway you don't need. But we will derive this later by using PV equal NKT and PV 1/m(c squared). I'll come to that point. Actual derivation is not in your syllabus. But anyway, you must know average kinetic energy of a gas particle is given by 3/2 kT, where k is called Boltzmann constant. So Boltzmann constant that is given in the data sheet, 1.38 into 10 to the power minus 34. Yeah, it's 10 to the minus 23 joule per Kelvin. So that's the Boltzmann constant value, 1.38, 10 to the power minus 23 joule per Kelvin. That's given in the data sheet. So that is the average kinetic energy of a gas particle. So average kinetic energy means, different gas particles at a particular temperature, they will be at different speeds. So how to represent this average kinetic energy in terms of average speed or average square of the speed, we call mean square speed. That's the thing we are going to do now. Okay, so assume that a closed container consists of n number of gas particles, capital N number of gas particles at a temperature T. So different gas particles will have different speed at an instant at that time. So the speeds could be V1, V2, V3 and so on. So we need a mean square speed because kinetic energy means half mv square. So here v square should be the average speed, it squares it. So mean square speed, we need that. So how to calculate the mean square speed means, if there are n number of gas particles with different speeds, v1, v2, v3 up to vn, Then the mean square speed, the notation is, this is the notation we use. Mean square speed means average of the squares. So mean square speed is given by V1 squared plus V2 squared plus V3 squared plus up to Vn squared divided by n. This is called mean square speed. So average kinetic energy means half m mean square speed. This is the average of the square. So mean square speed is the average when we calculate the means average kinetic energy of a molecule, half into mass of a gas particle or gas molecule into mean square speed, that is equal to 3 by 2 kT. So this is the first equation we got it in gas laws. Half mc squared equal to 3 by 2 kT, that is the average kinetic energy of a gas particle. So the total energy of the gas in a closed container, if there are n number of gas particles, so total kinetic energy, so we don't calculate the potential energy because we assume the gas behaves as ideal gas, so they don't have potential energy we take it. So the total kinetic energy of the gas, or we can say total internal energy of the gas, because we don't consider the potential energy. We treat even real gases as ideal gases up to certain extent at low pressure and high temperature. So the total kinetic energy is given by average kinetic energy into number of gas particles. So that means 3 by 2 kT into n, that is the average, total kinetic energy or total average kinetic energy, total average kinetic energy of the gas, not a molecule. Total average kinetic energy of the gas is given by 3 by 2 kT into n. Okay, so we know the mean square speed is given by V1 squared plus V2 squared up to Vn squared divided by n. That's the mean square speed of the gas particles. So what is the root mean square speed? R.m.s speed, square root of it. So that is denoted by c squared to the power half. Square root of these things. So that's the R.m.s speed, V1 squared plus V2 squared up to Vn squared divided by n, which is in square root. That is the root mean square speed. We call it as r.m.s speed. R.m.s speed. Okay, so first question in gases. There are 5 different gas particles and their speed at an instant are given. The question is, find the r.m.s speed of these gas particles. So r.m.s speed, you know, we need to square each of the gas speeds and divide by the number of gas particles and take the square root of it. So r.m.s speed is equal to square root of 500 squared plus 520 squared, 510 squared, 515 plus 490 squared divided by 5. Take the square root of it and solve it. You will get the final answer. So that will be 507.11. So we can say 507 meter per second. The unit of mean square speed, this is the r.m.s speed we found it. Unit of mean square speed is meter squared s minus 2. Square root of when you take, it becomes meter per second. Okay, so the second question, a closed container is filled with 1 mole of helium gas at a temperature of 20 degrees Celsius. 1 mole of helium gas consists of 6.0 to 10 to the power 23 Avogadro number helium molecules. Atomic mass of helium is given. That's the mass of one helium molecule is given. So find the total kinetic energy of the helium gas. So total kinetic energy means total average kinetic energy, we need to find it. So first part, kinetic energy of helium gas in the container is equal to 3 by 2 kT into Avogadro number of molecules. So that is going to be 3 by 2, K is 1.38, 10 to the power minus 23. Into temperature must be in Kelvin, so 20 degrees Celsius means 273 plus 20, 293. Number of molecules given Avogadro number, that is 6.02, 10 to the power 23, the unit is joules. Solve it, you will get the answer for the first part. So that will be 3651 or 50 joules. Second part, find the r.m.s speed of a helium gas molecule, root mean square speed of a helium gas molecule. So we know that half mc squared is equal to 3 by 2 kT. Half here 2 will get cancelled. So c squared, if you take its subject, c squared is going to be 3 kT over m. So I need to find the r.m.s speed. So take the square root of it, equal to square root of 3 kT over m. So that will be, it's continuing here. So this is the second part. So this is the end of first part. So that is going to be square root of 3, K is 1.38, 10 to the power minus 23. Temperature 293 over mass of a gas molecule 6.65. 10 to the power minus 27. Solve it. You will get the r.m.s speed, that is 1350 meter per second. Okay, so the third question, a closed cylinder contains gas at a temperature of 30 degrees Celsius. And r.m.s speed of a gas particle in the container is 510 meter per second. Find the r.m.s speed of a gas particle in this container, that means in this cylinder, at a temperature of 100 degrees Celsius. Okay, so we know that half mc square, where c square the mean square speed, square root of it gives the r.m.s speed. Half mc squared equal to 3 by 2 kT. So when the 2 gets cancelled, we'll get c squared equal 3k over m times t. Okay, we can answer by taking square root, but I feel some students have difficulty in handling square root. So I'll keep it in mean square speed. So r.m.s speed is given 510 means this is 510 squared. The same container, same mass of the gas particle. So it contains a gas, actually a gas, we can say a gas means a particular type of gas. K is constant. So T we know initially. We need to find the r.m.s speed at a particular temperature, 100 degrees Celsius. So at a temperature of 30 degrees Celsius, the r.m.s speed is 510. So mean square speed 510 squared equal 3k over m times, anyway it's a constant, I can replace it by k, a constant, but I will keep it as it is. Temperature is at 30 degrees Celsius, mean we have to convert to Kelvin scale. So 273 plus 30, 303, take it as first equation. So I need to find at 100 degrees Celsius, that is c square. I'm going to find the mean square, then I'll take the square root of it, is 3k over m into 100 degrees Celsius means 273 plus 100, 373, second equation. Okay, so we need to find the r.m.s speed. So divide second equation by first equation and take the square root of it. So that's going to be like this, c squared over 510 squared is equal to, when you divide second equation by first equation, 3k over m, 3k over m will get cancelled. You will get 373 over 303. So from this, solve it and get mean square, root mean square speed. Solve it and take square root of it. You will get That will be 566 meter per second. Okay, so the next is macroscopic properties of gas. What are the macroscopic properties of the gas? Means the quantities, those could be measurable, are called macroscopic properties. What are they? First one is temperature. Denoted by T. Second one is mass or mole or number of molecules. Or number of particles. We can say number of molecules or number of particles. That is the second macroscopic property. Third one, volume. Fourth one, pressure. Pressure exerted by the gas. Okay, so temperature of the gas, you know, temperature of the gas is due to average kinetic energy of the molecules or average kinetic energy of the particles of the gas is the reason for the temperature. I already told that before starting the specific heat capacity. Mass or molecule or number of particles also macroscopic property because it is measurable. Volume of the gas, careful, when we say volume of the gas is actually not the volume of the molecules, it's the volume occupied by the gas. We should say it like that, but anyway, sometimes students also say, even some books they say volume of the gas. Volume of the gas means, carefully listen, that is volume occupied by the gas. Volume occupied by the gas is called volume of the gas. We don't consider the actual volume of the gas molecules, that's the volume occupied by the gas. For example, if there is only one gas particle inside a container of volume 1 centimeter cube, we say the volume occupied by that only one molecule is 1 cm cube. Okay, so volume occupied by the gas, because gas particles are always in random motion. Then pressure exerted by the gas. Based on that, there were questions in the past paper, even in IGCSE. What's the reason for the pressure exerted by the gas particles? Okay, we can say the gas particles move randomly and they collide with the walls of the container. During the collision, the momentum of the gas particle will change. Due to rate of change of momentum, there will be force exerted on the gas particle. According to Newton's third law, the gas particle will exert the same magnitude of force on the walls of the container. Force per unit area is the pressure. So that's the reason for the pressure exerted by the gas on the walls of the container. Again, I am saying when a gas particles move randomly, gas particle will collide with the wall of the container. During collision, the momentum of the gas particle will change. The rate of change of momentum is the force experienced by the gas particle, because gas particle's momentum is changing. So the rate of change of momentum of the gas particle is the force experienced by the gas particle or force exerted on the gas particle. According to Newton's third law, the same magnitude of force will be exerted on the wall. Force per unit area is the pressure exerted by the gas. So that is the reason for pressure. Okay, so these are the macroscopic properties of the gas. So this is denoted by V, you know that. Pressure is denoted by P, symbol P. Temperature is T, number of molecules, mass is denoted by M, number of moles N, number of particles N. Either way we can use. Okay, now we are going to deal with gas laws. Boyle's law, pressure law, you had it in IGCSE. Charles law, not much comes. Then A level, we have only one new equation, PV equal NKT. Other than that, everything you will already learned in IGCSE. Okay, so by combining different macroscopic properties, we can obtain different gas laws. For example, first we consider the Boyle's law. We say Boyle's law means for a constant mass of gas at constant temperature. So that means we keep these two constant mass of gas at constant temperature, or constant number of particles of gas at constant temperature. We consider these two constant. When these two constants, then the only two macroscopic properties those can change is pressure and volume. How do they change? P1 V1 equal P2 V2, or PV equal constant. That's the way the macroscopic properties, pressure and volume changes. So by considering these two constant, we get the variation between pressure and volume. So that is the Boyle's law. Then pressure law, I'll come one by one, but anyway I'm just quickly summarizing what I'm going to do. Then pressure law means P1 over T1 equal P2 over T2, you learned that. So pressure law means for a constant mass of gas at constant volume, we consider these two constants. So earlier we consider first two constant, these two varied. Now these two constants, first and last going to vary. These two constants, first and last going to vary. P1 over T1 equal P2 over T2. Third one, Charle's law. There, what is constant? Constant mass of gas at constant pressure. So second and fourth remains constant. First and third are going to vary. V1 over T1 equal V2 over T2. Right. So far, pressure law, Boyle's law, Charle's law, there will be two constants and two variables. That's the way we came across. The next thing is, there could be one constant, other three can vary. What is it? That is the combined gas equation. P1 V1 over T1 equal P2 V2 over T2. So there, which is constant? That is the mass of the gas remains constant. All other quantities could change, means that is mass of the gas constant, all other quantities could change, means pressure, volume and temperature could change. So that gives the combined gas equation P1 V1 over T1 equal P2 V2 over T2. The last one, that is the A level, especially most of the questions come in that topic. Nothing is constant, anything can change. Anything can change. That means that is the ideal gas equation, or equation of state for ideal gas, that is PV equal NKT. There anything can change. So that is the and also the similar equation PV equal NKT, or we can get PV equal nRT. Both same. Here only the difference is number of molecules with Boltzmann constant, number of moles with universal gas constant. Both are actually another version of this one is this one. So that is nothing different. But your syllabus, mostly the question comes based on PV equal NKT, not on this one. Anyway, in which anything can change. That's the way the combinations are there. Okay, we'll analyze one by one. First, we'll deal with Boyle's law. Okay, you should be able to state the Boyle's law in words that you had it in or IGCSE also. For a constant mass of gas at constant temperature, pressure exerted by the gas is inversely proportional to its volume. Again, I'm saying, I'm not writing it. For a constant mass of gas at constant temperature, the pressure exerted by the gas is inversely proportional to the volume occupied by the gas. So that means pressure exerted by the gas is inversely proportional, means P proportional to 1 over V. When we convert it into a equation format, K times 1 over V, K is a constant. So PV equal constant. So that means P1 V1 equal P2 V2. So what's the meaning of it? For a constant mass of gas, say for example there is a cylinder which consists of piston out. So pressure of the cylinder, gas occupied inside the cylinder is P1 and the volume is V1. So if you multiply the pressure and volume, you will get a particular numerical value. Now you are compressing the gas, or you are moving the piston away. So when you compress the gas like this, if you move the piston closer, the volume will decrease. The volume becomes now V2. The pressure becomes V2. When you compress it, while the pressure increases, the gas particles are going to move in a smaller distance, so the rate of collision will increase. the rate of collision will increase. The number of collisions per second will increase, but each gas particles will carry the same kinetic energy because they are at the same temperature, but number of collisions per second will increase. So rate of collision increases means the total force exerted on the wall will increase. Pressure, force per unit area is the pressure. So more number of gas particles will hit at a particular instant. Say for example, when the volume is larger, the number of gas particles hitting or colliding with the wall per second may be 100. Now the volume decreases, number of gas particles colliding with the wall per second will be 200. So 200 gas particles are hitting on the wall per second means each gas particle will have the same average kinetic energy, but the force exerted by each gas particle on average could be same, but more number of collisions per second means each gas particle is exerting force in, the total force on the wall is more, so force per unit area is more, pressure is more. That's the reason when the volume decreases, pressure increases. So what's the meaning of the Boyle's law? Multiply the P1 into V1, P2 into V2, when the volume is reduced, you will get the same numerical value. That is the Boyle's law. So if you plot a graph for Boyle's law, you had it in O level also. Pressure against volume, so it's a PV equal constant. So PV equal constant means it's a hyperbolic graph. So this is volume, this is pressure. The graph will be a shape like this. It won't touch the both axes. This is at a particular temperature T1. You must know that when the temperature is higher but constant temperature, higher temperature but constant temperature, the graph will move out like this. This is at temperature T2, T2 greater than T1. That you must know. When the temperature is constant but higher temperature, if you draw the graph pressure against volume, say for example the first graph we plot at 20 degrees Celsius, different pressure and the correspond different volumes measured, and we plot the graph, that is the first graph for T1. Then you are doing the same practical at 30 degrees Celsius, higher temperature, but again you are doing the same practical for different volumes, you are measuring the different pressure, the corresponding pressure. When you plot the graph will have the same shape, hyperbolic graph, but it will be away from it. Okay. And also you know, if you plot a graph of pressure against 1 over volume, so you can see this equation, P equal a constant times 1 over V, that is in the form of y equal mx. So when you plot a graph here, pressure against 1 over volume, it's a y equal mx format. At temperature T1, which is lower, you will get a graph through the origin like this at temperature T1. At higher temperature, the same graph will pass through the origin but with larger gradient. So if there's a question like explain why pressure is inversely proportional volume at a constant temperature for a given mass of gas. If there's a question like this, you should say when the volume is reduced, the path the gas particles can follow or the distance the gas particles can move between opposite walls will decrease. The average kinetic of the gas particles will remain the same as earlier, but the distance they are going to travel or the length they are going to travel will decrease. Therefore, rate of collision with the wall will increase. When the rate of collision with the wall increases, rate of change of momentum, the total rate of change of momentum per on the walls, total rate of change of momentum will increase. Therefore, the total force exerted by the gas particles on the wall will increase. Force per unit area is the pressure. That's the reason pressure will increase. That's the answer you should give. Okay, so verifying the Boyle's law is not an issue. We have to use the Boyle's law apparatus. So this is the Boyle's law apparatus, standard apparatus. You can't make it, you have to buy it. So there's a terminal through that we can use a foot pump to insert air into it. So the air is inserted, it will compress the liquid. There's a liquid inside. So when it compresses, it will compress the trapped air here. We know the volume of the tube, which consists of trapped air, has a uniform area of cross section. So since the area of cross section of the trapped air is trapped air column is constant, uniform everywhere, means volume will be directly proportional to length of the trapped air column. Careful, volume is directly proportional to length of the trapped air column because the cross sectional area is uniform. So not a big issue. You insert a certain amount of air into the chamber by using a foot pump. Wait for a few minutes because when the trapped air is compressed, its temperature could change. So you have to wait until the temperature drops to room temperature. Record the length of the trapped air column and record the pressure gauge reading. Again, repeat, insert certain amount of air and again wait for a few minutes and record the length of the trapped air column and the pressure of the reading of the pressure gauge. Like that, take several readings. Then you are going to plot a graph of pressure against 1 over volume. But we know that volume is directly proportional to length because the area of cross section is uniform. So we can plot a graph of pressure, that means reading of the pressure gauge against 1 over length of the trapped air column. 1 over length of the trapped air column. Since volume is equal to length into area of cross section, uniform cross section area means volume is directly proportional to length. So you plot a graph and you will get a straight line through the origin. So since the graph is a straight line through the origin, I can say pressure is inversely proportional to length. But length is directly proportional to volume. Therefore, pressure is inversely proportional to volume. So pressure is equal to constant into 1 over V. PV equal K. That is the Boyle's law. We will verify the Boyle's law. Okay, so this question based on Boyle's law, how do we identify whether it's based on Boyle's law? We should be able to identify the variables and the constants. Say a cylinder A of volume 100 cm cube contains a gas at a pressure of 10 to the power 6 Pascal. So this is the cylinder A. It contains gas at a pressure of 10 to the power 6 Pascal. Cylinder B is vacuum. So inside the pressure is 0. It might contain the total mass of the gas is m. Now when you connect both cylinders by a tube which has negligible volume, higher pressure, lower pressure, the gas will flow from here to here. So the pressure of this cylinder will decrease, pressure of this will increase until both gets a new pressure, same new pressure, the gas will flow. Initially the mass of the gas here is m. Now finally after the flow at equilibrium, the mass here is m1, here m2. But we know that m1 plus m2 is equal to the same initial mass m. So here the volume is changing. Earlier the mass m is occupied only in 100 cm cube. Now the total mass m1 plus m2 is same mass is going to occupy in 300 cm cube. So the volume is increasing. No change in temperature, no change in total mass. So we have to use the Boyle's law. So Boyle's law means P1 over V, P1 V1 equal, P1 V1 equal, P2 V2. Initially the pressure 10 to the power 6 into 100 cm cube becomes P2 into 300. Find the P2, that's all. That's a new pressure. Inside both cylinders, the pressure will be the same. We have to consider the total mass is the same when we consider the whole system. So that will be 3.33 10 to the power 5 Pascal. That's a new pressure in both cylinders. Okay, next thing is pressure law. Pressure law says for a constant mass of gas at constant volume, pressure exerted by the gas is directly proportional to its absolute temperature. Absolute temperature means temperature in Kelvin scale. Careful, absolute temperature means temperature in Kelvin scale. Absolute zero temperature means 0 Kelvin, right? So the pressure law says for a constant mass of gas at constant volume, pressure exerted by the gas is directly proportional to its absolute temperature. Okay, how can we explain this based on motion of the particles. We can say when the temperature increases, average kinetic energy of the molecules or particles will increase. When the average kinetic energy of the particles increases, during collision, two things will happen. What are they? During collision, each and every particle will carry on average higher kinetic energy. So during collision, rate of change of momentum of each and every particle will be higher because they are going to hit the wall at higher speed, higher momentum. They'll bounce off. We take their elastic collision. So the change in momentum is higher now. Rate of change of momentum will be higher. So each and every particle will exert higher force or greater force when the temperature increases. One thing. The second thing, the rate of collision, the number of collisions per second also will increase because particles are moving at higher speed, means number of collisions per second with the wall will increase. So due to these two reasons, the force exerted on the wall will increase. So force per unit area is the pressure. So we can tell like this: when the temperature increases, average kinetic energy of the gas particles will increase. Therefore, during collision, each gas particle each gas particle have higher rate of change of momentum, and hence larger force will be exerted by each and every particle on the wall. Also, the total rate of collision, more number of gas particles will hit the wall per second. Due to these two reasons, the total force exerted on the wall will increase. Force per unit area is the pressure, so pressure will increase. Okay, so according to the pressure law, the pressure is directly proportional to absolute temperature. Absolute temperature means temperature in Kelvin scale. So P is equal to a constant times T. P over T is constant. That means P1 over T1 equal P2 over T2. Common mistake, mostly students, they don't convert the temperature to Kelvin scale. The temperature must be in Kelvin scale. Okay, so next we'll discuss how to verify the pressure law experimentally. Okay, so complete the setup as shown in the diagram. A flask consists of air. We assume air behaves as ideal gas. The flask should be kept inside water bath. The air should be connected to pressure gauge. So the pressure gauge measures the pressure of the air inside the flask. So there's a thermometer and there's a stirrer. So record the initially at room temperature. Initially the pressure gauge will read the pressure of the air, which is at room temperature. So heat the water, stir it well at different temperatures, record the pressure gauge reading. Then plot a graph of pressure gauge reading, that is the pressure of the air in the flask against temperature in Celsius scale. If you plot a graph of pressure against temperature in Celsius scale, the graph will not pass through the origin. So the graph will be a straight line, but it will intercept the temperature axis at minus 273.15. 273 we can take it. So here we can't say pressure is directly proportional to temperature. We can't say in Celsius scale because the graph is not passing through the origin. So that's the reason we say the temperature must be in Kelvin scale. But now when you convert the temperature to Kelvin scale, and if you draw the graph pressure against temperature in Kelvin scale, you should take at least 10 different readings, different temperatures and the relevant pressure of the air in the flask. Now if you plot a graph of pressure against temperature in Kelvin scale, it will be a straight line through the origin. So if the graph is a straight line through the origin, means pressure is directly proportional to temperature in Kelvin scale. So that's the reason we always say the temperature must be in Kelvin scale. If it is a Celsius scale, you can't use this equation because graph is not a straight line. It's a straight line but not passing through the origin. Now we will get this equation. Pressure is directly proportional to temperature. Pressure is equal to constant into T. So from that, pressure over T is equal to constant. So that means constant means for different pressure and the temperature, the ratio for a given mass of gas will remain constant. That is the pressure law. Okay, so this is simple question O level type. So P1 over T1 equal P2 over T2. So P1 is given 2 into 10 to the power 5. T1 is at Kelvin scale 273 plus 20, 293 equal P2 over T2, that is 60 plus 273, that is 333. Find the P2, that will be equal to 2.27 10 to the power 5 Pascal. Okay, Charles' law says for a constant mass of gas at constant pressure, volume occupied by the gas is directly proportional to its absolute temperature. So that means Charles' law says V proportional to T for a constant mass and constant temperature. So the T should be absolute temperature in Kelvin scale. So that means V is equal to K into T, that is V over T is constant. That is V1 over T1 equal V2 over T2 when mass and pressure remains constant. So horizontal cylinder consists of a frictionless movable piston and its area of cross section is 0.5 meters squared. At 20 degrees Celsius, pressure of the air in the cylinder is equal to atmospheric pressure. So if I consider the cylinder like this, it's a cylinder. So this is a cylinder. So there's a movable piston. So this is the air. The pressure is same as atmospheric pressure. So the pressure inside and outside are the same. It's a frictionless movable piston. So pressure inside and outside are the same, which is equal to atmospheric pressure. So the volume here is 2 meter cube. Area of cross section of the piston, movable piston, is 0.5 meters square. Okay, so by keeping it, the temperature of the air is increased to 70 degrees Celsius. Initially it was at a temperature of 20 degrees Celsius. So when the temperature of the air inside the cylinder is increased, you know, pressure will increase first because the air particles will move at higher kinetic energy. They will hit the movable piston, but there is no friction, so the piston will move until the pressure inside becomes equal to outside, because it's a frictionless movable piston. So when the pressure increases, when the temperature increases, yes, immediately, but when the pressure increases, the air particles will push the movable piston, the piston will move out, volume will increase. When the volume increases, pressure will again decrease until the pressure inside and outside becomes same as atmospheric pressure. So finally, when the temperature is stable at 70 degrees Celsius, again inside and outside is pressure same, but volume has increased. So pressure remains constant, the mass of the air inside the cylinder remains constant. So I can use Charles' law, V1 over T1 equal V2 over T2. So we use the Charles' law. If I use the Charles' law, V1 over T1 equal V2 over T2. So initially the volume is equal to 2 meter cube. Temperature is 20 degrees Celsius, means 293. We will find the new volume at a temperature of 70 degrees Celsius. So 70 degrees Celsius means it's equal to 343 Kelvin. So the volume will become, the new volume of the air inside, it was initially 2 meter cube. Now it has become 2.34 meter cube. So that means the increasing volume. So the piston has moved out. So I can imagine the piston has come to the new position somewhere here like this. So the distance it moved is L. So distance it moved is L. The area of cross section remains the same. So the change in volume or increase in volume is 2.34 minus 2, that is 0.34 meter cube. So increase in volume is equal to increase in length into area of cross section. So increase in volume is equal to increase in length, I can say delta L, that's the distance it moved, delta L into area of cross section. So delta V 0.34, delta L, the length it moved out, we need to find it. The area of cross section 0.5. So the distance it moved, the piston, the distance it moved, we can find, that is equal to 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . 0.68 . meters or 68 centimeter, it will move out. So since it's kept in horizontal position, the weight of the piston has no effect. Weight of the piston has no effect since the cylinder is kept in horizontal, a horizontal piston cylinder. Okay, so combined gas equation. We'll combine all these three gas laws: Boyle's law, pressure law, and Charle's law. So according to Boyle's law, PV equal constant. We'll let it be K1. So there the mass and temperature should remain constant. According to pressure law, P over T is equal to constant. Let it be K2, where mass and the volume should remain constant. According to Charle's law, V over T is equal to constant, K3 I can say. The mass and the pressure remains constant. Okay, so when we consider all these three, generally, the only one factor which remains constant throughout all three laws is the mass. So we'll multiply all these three by assuming all other factors are changing. So we'll multiply all these three. First, we'll multiply the left side, PV into P over T into V over T is equal to K1 into K2 into Kt. It's a constant again. So that means P squared, V squared over T squared equal to a constant. That means if we take square root, it becomes PV over T is equal to constant when mass of the occupied gas remains constant. So here, except mass, all three other macroscopic quantities can vary. That means P1 V1 over T1, P1 V1 over T1 equal to P2 V2 over T2, but mass remains constant. Okay, so here volume is changing, 4 meter cube initially, then the volume becomes 2.5. Pressure initially 1.8 10 to the power 5. The question is new pressure, but temperature is increasing from 30 to 50. So all three quantities are changing, nothing mentioned about mass or number of molecules. So it remains constant. So the only equation that we can use is combined gas equation, P1 V1 over T1 equal to P2 V2 over T2. So initially the pressure is 1.8 10 to the power 5. Volume is 4 over T1 should be in absolute temperature. So that is 30 degrees Celsius, means 273 plus 30, 303. The next pressure P2 is the question, we need to find it. Volume is now 2.5, it's compressed. And the temperature is 50, so that is 323. Find the P2, that's the new pressure of the air inside the cylinder. Okay, so ideal gas equation or equation of state for ideal gas, both actually the same equations in different formats. That means ideal gas equation in Edexcel questions won't come. Mostly the questions based on equation of state for ideal gas, but some other exam boards they use ideal gas equations. But anyway, ideal gas equation says PV equal nRT, where pressure, volume, number of moles, this is universal gas constant, temperature in Kelvin scales. Equation of state for ideal gas, PV equal nKT, where the difference is n is the number of gas particles or number of molecules. So K is the Boltzmann constant, T is the temperature, T is the temperature. Only these two are different. Number of moles, number of gas particles, universal gas constant, this is Boltzmann constant. But anyway, it's not an issue. If the question is given in terms of number of gas particles, and if you want to use this equation, you can convert the number of gas particles into number of moles by using N. The number of moles is equal to number of gas particles divided by Avogadro number, which is 6.02 10 to the power 23. Now, if the question is based on N, the question is given in terms of number of gas particles, and if you want to use the ideal gas equation, you can use this one, no problem, but only thing you need to find the relevant mole. So divide the given number of gas particles by Na, Avogadro number, which is 6.02 10 to the power 23. Or if, for example, the question is given in terms of number of moles and you want to use this equation, means multiply the number of moles by Avogadro number, then use this equation. So it's not a big issue, both are the same equations with different formats. Okay, so here N, number of moles, R means universal gas constant 8.3 joule per mole per Kelvin. Here N, you know, number of gas particles. K is Boltzmann constant. I already gave, that is 1.38 10 to the power minus 23. So it's not an issue. Either equation you can use, no problem. But Edexcel, better use this equation because mark scheme, the mark scheme carries this one. But other examples, they can use this one. But only thing, if you want to convert number of gas particles to number of moles, use this one. Number of moles equal N over Na, then use this equation. But when you are using this, you have to use R, which is 8.31. If you are using this one, K, Boltzmann constant, that's the only difference. Okay, so this is the first question based on equation for ideal gas, equation of state for ideal gas. Okay, the volume of the cylinder given, pressure of the hydrogen gas in the cylinder is given, and the temperature is given. By keeping the temperature constant, additionally, extra this number of molecules of hydrogen is inserted into the cylinder. Find the new pressure. Okay, anyway, PV equal NKT. You can use PV equal nRT also, no problem, but only thing you need to find the number of moles which is equivalent to this number of molecules. Then you can use PV equal nRT, you will get the final answer the same, nothing will go wrong. But I'll use PV equal NKT because Edexcel mostly they give the answer in terms of PV equal NKT. So when we want to find the final pressure, we should know the total number of hydrogen molecules after this number of molecules is inserted into the cylinder. So we should know the initial number of molecules in the cylinder. With that we add it, we will get the final number of molecules. So we'll use PV equal NKT for initial state. So N1 initially PV over KT. So pressure we know initially, that is 1.2 10 to the power 5. Volume we know 3. K 1.38 10 to the power minus 23 into temperature 20 degrees Celsius 293 Kelvin. So find the initial number of hydrogen particles in the cylinder, which is 8.90 10 to the power 25. Now finally the number of molecules is, we have to add with this number of molecules. So 8.90 10 to the power 25 plus 4.8 into 10 to the power 25, that will be equal to 1.37 10 to the power 26. Now use PV equal NKT to find the final pressure. So P2 that we are going to find, N2 that is 1.37 10 to the power 26, K 1.38 10 to the power minus 23. Temperature remains constant, so 293 divided by volume, that is 3. Solve it, you will get the final you will get the final pressure, that will be 1.85 10 to the power 5 Pascal. Again, those who want to do PV equal nRT, no problem. You can use PV equal nRT instead of PV equal NKT and find the number of moles initially in the cylinder, then convert this to number of moles divided by Avogadro number. You will find the number of moles inserted into the cylinder. Add both moles, what you find here with this number of moles, then use PV equal nRT again. You will get the same answer, nothing will go wrong. Okay, so the second question, a closed cylinder of volume 1.5 meter cube contains helium gas at a pressure of 1.6 10 to the power 5 Pascal and at a temperature of 30 degrees Celsius. When the pressure exceeds 2 into 10 to the power 5 Pascal, so if the pressure becomes more than 2 into 10 to the power 5 Pascal, a safety valve opens and releases gas. Find the number of helium molecules released from the cylinder when the temperature increases to 160 degrees Celsius. Okay, we'll just check whether the pressure becomes more than 2 into 10 to the power 5 when the temperature becomes 160. But you don't need to write it in the exam. But we'll check whether it's correct. So imagine if the safety valve is not functioning, then pressure will be P1 over T1 equal P2 over T2. We can use pressure law because volume is not changing, no release of, in case if the safety valve is not functioning. So what could be the pressure? Will it become more than this? We'll check it. Just then we'll go to the proper way of answering. You don't need to write this in the exam, just we are checking it. So initial pressure is 1.6 10 to the power 5. Volume, temperature is 30 means 303 equal to P2 over 160 means that will be 433. Find the P2. You will see the P2 will be 2.29 10 to the power 5 Pascal. So that means it's more than the safety value of pressure. So certainly the valve should release because the pressure will become, if the valve is not working, pressure will become this one. So it might explode or burst or whatever it is. So there we need to find the number of molecules released. So certainly the valve will function and it's going to release. So number of molecules released means we have the equation for number of molecules remaining in the cylinder. PV equal NKT. N is the number of molecules in the cylinder. So initially I can say P1 V, the volume is not changing, equal to N1 K T1. So from this I can say N1 is the initial number of molecules. N1 is equal to P1 V over K T1. Same way, after it is released, the number of molecules remaining in the cylinder, if I take N2, N2 will be equal to, after it's released, the N2 is equal to P2 V over K T2. Is it? After it's released. So number of molecules released means number of molecules released from the cylinder. Initially N1 number of molecules were there. Finally pressure becomes P2, that means it can't exceed more than this. So the pressure could be 2 into 10 to the power 5. Volume is the same, no change because volume of the cylinder is fixed. K, the temperature has become 160. So the N2 is the number of molecules going to remain in the cylinder. So the number of molecules released will be N1 minus N2. So that is N1 minus N2 means P1V over K T1 minus P2V over K T2. Right. So substitute, you will get the answer. So we know all the quantities. So V and K are constant. If you want, you can take it out. It's up to you. So V and T, you can take it out. That means it's maths, not a big issue. V over K. Sorry, V and K are constant. V over K. T1 over T1 minus T2 over T2. Solve it. Okay. So we know the volume. That is not changing. That 1.5. K 1.38. 10 to the power minus 23. Pressure, initially the pressure was at 2 into 10 to the power, 1.6 10 to the power 5 over temperature 303 minus P2, it can't exceed 2 into 10 to the power 5, the safety value 2 into 10 to the power 5 over temperature 160, that is 433. solved it, that will give the number of molecules escaped. That will be equal to 7.19 10 to the power 24 molecules will escape. Okay, so equation for kinetic air of gas, this based on that there were no questions in the past paper, but I just do it because as an A2 syllabus they might introduce this and ask question. They can give this equation in the question, not in the data sheet, with the question, and they can ask you to find certain quantities like density or anything. So I'll give the equation. So the equation is derived actually purely by using Newtonian mechanics. So ideal gas means the particles, those are rigid, the collision is perfectly elastic. By using rate of change of momentum is equal to force and those concepts, purely by using Newtonian mechanics, we can derive an equation for ideal gas, EV equal 1/3 mnc squared. Pressure, volume occupied by the gas, mass of a gas particle or gas molecule, number of gas molecules, that's the mean square speed. All quantities you know, but derivation is not in your syllabus. Even this equation is not in the syllabus, but sometimes as A2 paper they might introduce an ask, so that's the reason I am giving it. Okay, so by using it they can ask you to find the density of a gas at a particular for a particular pressure. So this is mass of a gas particle or molecule, total number of molecules. So Mn is the total mass, is it? Mass of a gas molecule in the number of molecules in the container is the total mass of the gas. So pressure is equal to 1/3 Mn over V into C squared. So Mn over V, total mass over volume is the density. So 1/3 rho C squared. So they can ask you to find the density by using this equation. Not a big thing. They can ask you to derive it. So not a nothing complication. So you can derive this equation. Also, they can give a numerical value. Pressure could be given, mean square scale could be given. They can ask you to find the density, is it? So not a big issue. Just I am doing it. Secondly, you must know that we can get the equation for average kinetic energy of a molecule by combining this equation PV equal 1/3 Mn C squared, and by using PV equal NKT. If I combine these two, left side is PV, so right side should be same. So therefore 1/3 Mn C squared equal NKT. Okay, so n will get cancelled, so that will become, so I will continue here, 1/3 mc squared equal to kT. Okay, so multiply by 3, so mc squared equal 3 kT. Divide by multiply by half mc squared. That's the average kinetic energy of a gas particle. Half mc squared is equal to 3/2 kT. So they can ask you to derive this equation also. Okay, so that's all. I have completed the thermodynamics in one lesson. I hope it will be useful to you. Okay, you can, I think it will be useful to you. Yeah, right. Okay, so bye.